Hello and welcome. I'm so glad you're here with me tonight. Find a comfortable position wherever you are. Let your shoulders drop, release any tension you might be holding in your jaw, and take a slow, deep breath. Hold it for just a moment, then now let it go. Tonight we're going on a journey together, a peaceful exploration into one of the most beautiful and fundamental concepts in all of mathematics. We're going to discover how polynomials, these elegant mathematical expressions, are woven into the very fabric of our universe. But don't worry if mathematics hasn't always been your favorite subject. Tonight there are no tests, no pressure, no rushing. We're simply going to wander through ideas together, at a pace that feels calm and natural. Think of this time as a gift you're giving yourself, a chance to let your mind drift through the cosmos of mathematical thought, to see patterns and connections that have been hiding in plain sight all along. The exponential function rises with a persistence that defies ordinary growth. Where linear increases march forward and steady steps and quadratic curves bend gradually upward, the exponential explodes into territories that seem almost unnatural in their acceleration. To raise a number to a power means to multiply that base by itself repeatedly. And when that power itself grows, when x becomes the exponent rather than the base, we enter realms where intuition stumbles and magnitude becomes almost meaningless. Consider e raised to the power of x, where e represents that mysterious constant approximately equal to 2.71828. This number emerges from the study of continuous growth, from compound interest calculated at every infinitesimal moment, from the derivative that equals its own function. When we write e to the x, we describe a function that at every point grows at a rate proportional to its current value. The slope at any location equals the height at that location. This self-reference creates a feedback loop of increase, a mathematical echo chamber where growth begets more growth. The journey begins gently enough. When x equals -3, e to the power of -3 yields approximately 0.05. The function hugs the horizontal axis, barely distinguishable from 0. Moving rightward, at x equals -2, we find e squared in the denominator, giving roughly 0.14. Still small, still contained. At -1, e to the -1 equals 1 divided by e, approximately 0.37. The curve begins its turn upward. At the origin, where x equals 0, something beautiful occurs. Any number raised to the 0 power equals 1, and e to the 0 is no exception. The function crosses the vertical axis at unity, at the point where horizontal and vertical meet in perfect coordination. This serves as the anchor, the reference point from which all other values derive their meaning. At the positive territory, the transformation accelerates with breathtaking speed. At x equals 1, we simply have e itself approximately 2.72. Already we've nearly tripled from the origin. At x equals 2, e squared gives approximately 7.39. The gap widens. At 3, e cubed reaches roughly 20.09. At 4, we touch 54.6. At 5, 148.4. The distances between consecutive integer values grow exponentially themselves. From 0 to 1, we gain 1.72 units. From 1 to 2, we gain 4.67 units. From 2 to 3, 12.7 units. From 3 to 4, 34.5 units. Each step covers more ground than all previous steps combined, stretched and magnified. This pattern extends infinitely. At x equals 10, e to the 10th reaches 22,000 and change. At 15, over 3 million. At 20, we breach 480 million. The numbers become abstractions, collections of digits that no longer connect to tangible quantities. We speak of billions, trillions, values that dwarf human experience. The inverse relationship holds equal fascination. For negative x values, e raised to -x equals 1, divided by e to the x. This creates a mirror image, a reflection across the vertical axis, where decay replaces growth. The function approaches 0 asymptotically, getting closer and closer, but never quite touching, never reaching that ultimate terminus. At x equals -10, we find a number so small it requires scientific notation to express, meaningfully, approximately 0.000454. Between these extremes lies the full spectrum of exponential behavior. The continuous nature of e to the x means we can evaluate it at any real number, not just integers. At x equals 1/2, e to the 1/2 equals the square root of e, approximately 1.65. At 3/2 we get roughly 4.48. The function flows smoothly, without breaks or jumps, tracing an elegant curve that sweeps from near zero on the left to unbounded heights on the right. The derivative of e to the x with respect to x equals e to the x itself. This remarkable property makes the exponential function its own rate of change. If we imagine a particle moving along a path where its velocity at any instant equals its position, we describe exponential motion. The particle accelerates continuously, its speed increasing in direct proportion to how far it has traveled. The self-reinforcing dynamic appears throughout nature. In population growth when resources remain unlimited. In nuclear chain reactions. In the spread of information through social networks. Integration reveals the same pattern. The integral of e to the x, with respect to x equals e to the x, plus an arbitrary constant. The antiderivative matches the original function. This symmetry between differentiation and integration distinguishes the exponential from other elementary functions, creating a mathematical object that remains invariant under the fundamental operations of calculus. We can shift and scale the exponential to create families of related functions. Multiplying by a constant, a gives a times e to the x, which stretches the graph vertically. The y-intercept moves from 1 to a, but the fundamental shape persists. Every point rises or falls by the same factor, preserving the exponential character. Adding a constant to the exponent creates horizontal shifts. The function e raised to the quantity x minus h translates the entire graph h units to the right, if h is positive, or left if h is negative. The zero crossing moves, the point where the function equals 1 relocates, but the essential behavior remains unchanged. We still have exponential growth, just centered at a different location. Multiplying the exponent by a constant k yields e raised to kx, which affects the rate of growth. When k exceeds 1, growth accelerates even faster. When k lies between 0 and 1, growth slows but continues. Negative k produces exponential decay, mirroring growth with decline. These variations allow us to model different scenarios, different speeds of change, while maintaining the core exponential structure. The natural logarithm serves as the inverse of the exponential function. If y equals e to the x, then x equals the natural logarithm of y. This relationship allows us to solve exponential equations, to unpack growth, and find the time required to reach specific values. The logarithm converts multiplication into addition, powers into products, providing tools to linearize exponential relationships and render them more tractable. Compound interest provides a classic application. When money grows at a continuous rate, r, the value at time t equals the initial principal, p times e raised to rt. The exponential captures the effect of constant percentage growth, where each increment builds on everything that came before. A savings account, a viral video, a pandemic spreading through a population, all follow this basic template when unchecked by external constraints. The exponential distribution in probability theory uses e raised to negative lambda x to model waiting times between events in a Poisson process. Here the exponential decay represents the likelihood of longer intervals, with most events occurring relatively quickly, and rare instances stretching far into the future. The memoryless property emerges from the exponential form. The probability of waiting an additional unit of time remains constant, regardless of how long we've already waited. In physics, radioactive decay follows exponential patterns. The number of unstable atoms at time t equals the initial count, times e raised to negative lambda t, where lambda represents the decay constant. Half-life derives from solving for the time when this expression equals 1/2 the original amount, connecting exponential decrease to observable physical phenomena. Temperature equilibration obeys Newton's law of cooling, where the temperature difference between an object and its surroundings decreases exponentially over time. A hot coffee cooling in a room, a frozen dinner thawing on the counter, both trace exponential curves as they approach ambient temperature. The rate of heat transfer at any moment depends on the current temperature gap, creating the self-referential dynamics characteristic of exponential processes. Electrical circuits containing capacitors or inductors exhibit exponential charging and discharging. When a capacitor charges through a resistor, the voltage across the capacitor grows as 1 minus e raised to negative t divided by RC, where RC represents the time constant. The current decays exponentially as the capacitor fills. Discharging reverses the process, with stored energy dissipating, according to an exponential decay law. The catenary curve, the shape assumed by a hanging chain or cable under its own weight, involves hyperbolic cosine, which can be expressed as 1/2 times the sum of e to the x and e to the negative x. This combination of growth and decay creates the graceful arc we see in suspension bridges and power lines, where material properties and gravitational forces find equilibrium in exponential relationships. Probability distributions like the normal distribution, though not purely exponential, incorporate e raised to negative x squared. The Gaussian curve's bell shape arises from exponential decay of the square of the distance from the mean, creating the ubiquitous pattern we find in measurement, errors, natural variations, and countless statistical phenomena. The gamma function, which extends factorial to non-integer values, requires integrating t raised to x minus 1 times e to the negative t from 0 to infinity. The exponential term ensures convergence, taming the polynomial growth, then allowing the integral to exist for positive x values. This interplay between polynomial and exponential behaviors characterizes many special functions in mathematical analysis. Laplace transforms convert differential equations into algebraic equations. By integrating functions multiplied by e raised to negative saint, the exponential weighting privileges certain frequencies, transforming time domain problems into frequency domain solutions, where analysis becomes more straightforward. Engineers use Laplace transforms to study control systems, signal processing, and circuit analysis. The moment-generating function and probability, defined as the expected value of e raised to tx, encodes all moments of a distribution when they exist. Taking derivatives at t equals 0 extracts mean, variance, skewness, and higher moments, providing a compact representation of distributional properties through exponential machinery. Stirling's approximation for large factorials uses exponentials to simplify unwieldy products. For large n factorial approximately equals the square root of 2 pi n times the quantity n divided by e raised to the power n. This exponential approximation makes calculations feasible and reveals the asymptotic behavior of factorial growth. The binomial distribution approaches the Poisson distribution in certain limits, the convergence mediated by exponential functions. When the number of trials grows large, while the probability of success per trial shrinks proportionally, the discrete binomial converges to the continuous Poisson, whose probability mass function involves e raised to negative lambda. In economics, exponential growth models capture idealized market expansions, though real economies face constraints that eventually impose bounds. The assumption of constant percentage returns leads to exponential projections, useful for short-term forecasting, but requiring modification for long-term accuracy. The exponential provides a baseline, a limiting case against which actual growth can be measured. Population models frequently begin with exponential assumptions. Malthusian growth, where population increases proportional to current size, yields exponential solutions. Of course, real populations encounter resource limitations, predation, disease, and other density-dependent factors that modify simple exponential dynamics. The logistic equation introduces carrying capacity, bending exponential growth into an S-curve that saturates at environmental limits. Epidemiological models during the early stages of disease outbreaks often show exponential increase in cases. Each affected individual potentially infects multiple others, creating chains of transmission that multiply geometrically. Public health interventions aim to break these chains, reducing the effective reproduction number below 1, and transforming exponential growth into exponential decay. The mathematics of compound interest demonstrates exponential accumulation of wealth. When interest compounds continuously at rate r, the future value equals the present value times e raised to rt. This explains the power of long-term investing, where time and compound returns interact exponentially to build substantial assets for modest initial contributions. Information theory uses exponential functions in entropy calculations. The Shannon entropy of a discrete probability distribution sums terms of the form negative p times the logarithm of p, where p represents probability. Since logarithms invert exponentials, this formulation quantifies uncertainty through exponential-related expressions, measuring the average information content of messages from a source. Thermodynamics employs the Boltzmann distribution, or the probability of a system occupying a state with energy E is proportional to e raised to negative e divided by kT, with k representing Boltzmann's constant and T absolute temperature. Higher energy states become exponentially less likely at lower temperatures, explaining phase transitions and thermal equilibrium. Chemical kinetics relies on the Arrhenius equation, which states that reaction rate constants depend on E raised to negative activation energy divided by RT. Temperature appears in the denominator of the exponent, so higher temperatures exponentially increase reaction rates by allowing more molecules to overcome energy barriers. This exponential sensitivity explains why small temperature changes can dramatically affect reaction speeds. The Black-Scholes model for option pricing incorporates exponential terms in its solution for call input values. The model assumes stock prices follow geometric Brownian motion, with returns distributed log-normally, connecting exponential functions to financial derivatives and risk management. Queuing theory models waiting lines using exponential distributions for arrival times and service durations. The memoryless property simplifies analysis, allowing elegant solutions for average wait times, queue lengths, and system utilization in MM1 and related queues. Survival analysis in medical statistics often assumes exponential or related distributions for time-to-event data. The hazard rate, representing instantaneous risk of failure, can remain constant, exponential, increase or decrease, depending on the underlying distribution chosen to fit observed survival curves. The Poisson process, fundamental to stochastic modeling, generates events randomly in time, with exponentially distributed inter-arrival times. This mathematical idealization approximates many real phenomena. Phone calls arriving at a switchboard, cosmic rays striking a detector, customers entering a store during off-peak hours. Buffon's needle problem, though geometric, connects to exponential functions through probability calculations. The likelihood of a randomly dropped needle crossing parallel lines depends on trigonometric integrals that can be expressed using exponential forms of sine and cosine through Euler's formula. Speaking of Euler's formula, e raised to ix equals cosine x plus I times sine x, uniting exponential, trigonometric, and complex numbers in one stunning equation. This relationship allows us to represent rotations as complex exponentials, simplifying Fourier analysis and signal processing. The exponential spiral in the complex plane traces circles when purely imaginary exponents combine with real-time parameters. Fourier transforms decomposed functions into frequency components, using integrals weighted by e raised to negative 2 pi I times frequency times time. This exponential kernel extracts sinusoidal content at each frequency, transforming temporal patterns into spectral representations essential for audio processing, image analysis, and quantum mechanics. The Schrödinger equation in quantum mechanics is often solved using exponential ansatz. Wave functions frequently involve e raised to ikx for plane waves or e raised to negative r squared for ground state solutions, with exponential behavior reflecting the probabilistic nature of quantum systems and the uncertainty principle's fundamental constraints. Perturbation theory and quantum field theory expands scattering amplitudes in series involving exponential factors from propagators and interaction vertices. Feynman diagrams encode these exponential contributions, with each term representing quantum mechanical amplitudes that interfere constructively or destructively. The partition function in statistical mechanics sums e raised to negative beta times energy over all possible states, where beta equals 1 divided by kt. This exponential weighting generates thermodynamic quantities through derivatives, connecting microscopic state probabilities to macroscopic observables like free energy, entropy, and specific heat. Path integrals in quantum mechanics and quantum field theory integrate over all possible paths, weighted by e raised to I times action divided by h bar. The exponential of the action, a functional of the path, determines quantum amplitudes, with classical paths corresponding to stationary phase contributions. Exponential functions appear in solutions to the harmonic oscillator, where linear restoring forces lead to sinusoidal motion, expressible through complex exponentials. The energy eigenstates of quantum harmonic oscillators involve Hermite polynomials multiplied by Gaussian exponentials, forming a complete basis for quantum states. Diffusion equations governing heat flow and concentration gradients have solutions involving exponential time decay multiplied by spatial patterns. The heat kernel, fundamental solution to the heat equation, combines exponential time dependence with Gaussian spatial spreading, describing how initial temperature distributions evolve. The Ornstein-Uhlenbeck process models mean reverting stochastic dynamics using exponential relaxation to equilibrium. This process appears in finance for interest rate models, in physics for Brownian motion and a potential well, and in biology for fluctuating gene expression levels. Exponential random graphs in network science model the probability of observing a particular network structure as proportional to e raised to a linear combination of network statistics. These models capture clustering, degree distributions, and other structural properties through exponential weighting of configurations. Machine learning often uses exponential functions in activation functions and loss calculations. The softmax function converts real-valued scores into probabilities using exponentials in both numerator and denominator. Cross-entropy loss, commonly used for classification, involves logarithms of probabilities inverting the exponential relationship between scores and class likelihoods. Neural networks with sigmoid activation functions use 1 divided by 1 plus e raised to negative x, which ranges from 0 to 1 and provides smooth differentiable nonlinearity. The derivative of the sigmoid equals the sigmoid times 1 minus itself, a property that simplifies backpropagation calculations. Exponential smoothing and time series forecasting weights recent observations more heavily using exponential decay of older data. The smoothing parameter determines how quickly influence fades, with each step backward in time, multiplying the weight by a constant factor less than 1. Reinforcement learning uses exponential discounting of future rewards, where immediate rewards count more than delayed ones. The discount factor, raised to increasing powers for rewards further in the future, creates exponential temporal preference that balances immediate gratification against long-term planning. Benford's law, describing the distribution of leading digits in many natural occurring datasets, emerges from scale invariance arguments involving logarithmic and exponential relationships. Data spanning multiple orders of magnitude tends to favor smaller leading digits, a pattern explained through exponential growth and multiplicative processes. The gamma distribution, used to model waiting times for multiple events, has probability density involving x raised to shape minus 1 times e raised to negative x divided by scale. This flexibility allows fitting various skewed positive distributions encountered in reliability analysis and survival studies. The Weibull stipule, wisely used for wily use for failure analysis, contains exponential terms in both its cumulative distribution and hazard functions. When the shape parameter equals 1, it reduces to the exponential distribution, but other shape values capture increasing or decreasing failure rates over time. Extreme value theory employs the Gumbel distribution, whose cumulative distribution function involves a double exponential, e raised to negative e raised to negative the standardized variable. This distribution models maximum or minimum values from large samples, applicable to flood heights, wind speeds, and other environmental extremes. The logistic function, closely related to the exponential, equals 1 divided by 1, plus e raised to negative x. This S-shaped curve transitions smoothly from 0 to 1, modeling growth with saturation limits. Logistic regression and statistics uses this function to convert linear combinations of predictors into probabilities. The hyperbolic functions sin and cosh, defined as combinations of e to the x and e to the negative x, appear in solutions to differential equations, with different symmetries than their trigonometric cousins. The hyperbolic tangent tanh serves as an activation function in neural networks, ranging from -1 to +1, with convenient derivative properties. Continued fractions provide alternative representations for e and related quantities. The simple continued fraction for e exhibits patterns in its terms, offering insights into the number's arithmetic properties and connections to numbers theory. The Champernowne constant, formed by concatenating consecutive integers, has been proven transcendental using properties of exponential functions and Diophantine approximation. The exponential function's transcendence, established by Hermite and Lindemann, underlies many results about which numbers can be roots of polynomial equations. Exponential sums in analytic number theory, where we sum e raised to 2 pi I times some function of integers, encode information about prime numbers, divisor functions, and other arithmetic properties. The circle method uses exponential sums to count integer solutions to Diophantine equations. The Riemann zeta function, central to the distribution of prime numbers, can be expressed using integrals involving exponential terms. The functional equation relating zetas to zeta 1 minus s involves gamma functions, which themselves require exponential integrals for definition. Generating functions in combinatorics often involve exponential functions, particularly when counting labeled structures. The exponential generating function for the sequence a sub n equals the sum over n of a sub n times x to the n divided by n factorial, with the factorial denominator creating exponential growth patterns. The Catalan numbers, counting various combinatorial structures, like binary trees and polygon triangulations, have an exponential generating function involving modifications of the exponential function. The growth rate of Catalan numbers is exponential, with the nth number approximately equal to 4 to the n divided by n to the 3/2 times the square root of pi. Asymptotic analysis frequently employs exponential functions to describe growth rates. Bédot notation classifies algorithms by their scaling behavior, with exponential time complexity, indicating impractical computation for large inputs. Understanding exponential growth helps algorithm designers avoid intractable approaches. The Fibonacci sequence, though defined recursively by addition, has a closed form involving powers of the golden ratio phi, approximately 1.618. The Fibonacci number equals phi to the n minus its conjugate to the n, all divided by the square root of 5. This exponential formula reveals why Fibonacci numbers grow so rapidly. Chaos theory studies systems exhibiting sensitive dependence on initial conditions, often described by exponential separation of nearby trajectories. The Lyapunov exponent quantifies the sensitivity, measuring the average exponential rate at which small perturbations grow. Positive Lyapunov exponents indicate chaos. Fractals frequently involve exponential scaling relationships. The Hausdorff dimension of a self-similar fractal can be calculated from the ratio of logarithms of scaling factors, connecting exponential relationships between size and number of pieces to non-integer dimensionality. The logistic map, a simple discrete dynamical system, exhibits period doubling root to chaos as a parameter increases. The bifurcation diagram shows regions of stability separated by exponentially narrowing windows, with the Feigenbaum constant characterizing the universal rate of convergence. Percolation theory studies connected components in random graphs and lattices, with phase transitions occurring at critical probabilities. The cluster size distribution near criticality often follows power laws, but far from the critical point, exponential decay dominates. Random walks in one dimension have expected distance from origin growing as the square root of time, but the probability of returning to go. Origin evolves exponential functions through the central limit theorem. Higher dimensional random walks show different behavior, with exponential factors appearing in various probability calculations. The birthday paradox, where probability of shared birthdays reaches 50%, with just 23 people, involves exponential calculations. The probability that all birthdays differ equals the product of terms involving 365 minus k divided by 365, which for large groups approximates e raised to negative k squared divided by 730. Kukan collector problems, asking how many random draws are needed to collect all items in the set, have expected completion times involving harmonic numbers, which grow logarithmically. The logarithm, inverse of the exponential, appears throughout probabilistic waiting time analysis. Secretary problems and optimal stopping theory use exponential discounting to balance exploration and exploitation. The probability of selecting the best candidate under various strategies involves exponential terms and cumulative distribution functions. Quantum tunneling probabilities depend exponentially on barrier properties. A particle encountering a potential barrier has tunneling probability proportional to e raised to negative 2 times the integral of kappa dx, where kappa involves the square root of barrier height minus particle energy. This exponential sensitivity explains radioactive alpha decay and scanning tunneling microscopy. The cosmological constant in general relativity, if positive, leads to exponential expansion of the universe. Dark energy accelerates cosmic expansion, with scale factor growing as e raised to Hubble constant times, time in the limit of constant dominated expansion. This exponential stretching will eventually isolate galactic clusters beyond each other's cosmic horizons. Black hole thermodynamics assigns entropy proportional to horizon area, with temperature inversely proportional to mass. The Hawking radiation spectrum follows a Planck distribution, evolving exponential factors, causing black holes to evaporate over exponentially long timescales. String theory amplitudes involve exponential factors from worldsheet actions and vertex operator insertions. The Veneziano amplitude, describing four-particle scattering, contains gamma functions in both numerator and denominator, connecting to exponential integrals through their definitions. Renormalization group flows in quantum field theory often exhibit exponential running of coupling constants. The beta function governing how couplings change with energy scale can drive parameters to grow exponentially toward strong coupling, or decay toward weak coupling at high energies. Inflation in early universe cosmology posits a brief period of exponential expansion, where the scale factor grows as e raised to Hubble parameter times time. This exponential stretching solves the horizon and flatness problems by smoothing initial conditions across vast distances. The Unruh effect predicts that accelerating observers detect thermal radiation with temperature proportional to acceleration, involving exponential Boltzmann factors in the distribution. This connects acceleration to temperature through exponential relationships in quantum field theory in curved spacetime. Hawking radiation from black holes involves exponential Boltzmann suppression of high-energy modes. The resulting thermal spectrum causes black holes to lose mass over time, with evaporation rate accelerating as mass decreases, ultimately culminating in explosive final moments. The holographic principle, relating bulk physics to boundary theories, involves exponential suppression of non-conformal operators in the AD-CFT correspondence. Correlation functions decay exponentially, with separation in the bulk theory's radial direction. Complexity theory in black hole physics introduces quantum complexity, measuring the difficulty of preparing quantum states. Growth of complexity appears to be linear for exponentially long times, eventually saturating at values exponentially in entropy. Matrix models in string theory and random matrix theory involve exponential factors in partition functions. The Gaussian unitary ensemble has probability measure proportional to e raised to negative trace of matrix squared, generating universal correlations between eigenvalues. Topological field theories assign partition functions to manifolds using exponential weightings of field configurations. Chern-Simons theory, for instance, has action involving the integral of Chern-Simons form, leading to exponential path integral contributions. Supersymmetric quantum mechanics often has exact solutions involving exponential superpotentials. The ground state wave function can involve e raised to integral of superpotential, with supersymmetry constraining the form of allowable potentials. Instantons in quantum field theory and quantum mechanics represent tunneling amplitudes between different vacuum states, calculated as e raised to negative action divided by coupling constant. These exponentially suppressed contributions can nonetheless dominate certain processes in strongly coupled theories. Solitons and kinks in nonlinear field theories often have profiles involving hyperbolic tangent or secant, combining exponential growth on one side with exponential decay on the other. These coherent structures propagate without dispersion, maintaining their exponential tail behavior. The Lambert W function, inverse of x times e to the x, appears in solutions to transcendental equations involving exponentials. This special function, though less familiar than logarithms, proves essential for certain growth models and delay differential equations. Delay differential equations, where derivatives depend on past values, often have solutions involving exponential terms with complex exponents. The spectrum of delays and coupling strengths determines stability through characteristic equations requiring exponential ansatz. Fractional calculus extends derivatives and integrals to non-integer orders, with the Riemann-Liouville fractional integral defined through convolution with power law kernels related to incomplete gamma functions. Exponential functions appear in Laplace transform solutions to fractional differential equations. Mittag-Leffler functions generalize the exponential function to fractional calculus contexts, defined as infinite series involving quotients of arguments to various powers divided by gamma functions. These functions reduce to exponentials in special cases, while capturing stretched exponential relaxation in others. Kohlrausch-Williams-Watts stretched exponential decay, involving e raised to negative time divided by tau raised to beta, models relaxation in complex systems like glasses and polymers. The stretching parameter beta less than 1 indicates distribution of relaxation timescales, a departure from simple exponential behavior. Anomalous diffusion in complex media shows mean squared displacement growing nonlinearly with time, described by fractional diffusion equations with solutions involving Mittag-Leffler functions rather than pure exponentials. This generalizes normal diffusion's exponential spreading. Levy flights and Levy processes exhibit power law jump distributions, rather than exponential, leading to superdiffusive behavior. The characteristic function of Levy's stable distributions involves exponential of absolute argument raised to stability index alpha, generalizing Gaussian exponential of squared argument. The Zith distribution for Reich frequency relationships follows power law, rather than exponential decay, yet generating functions involve polylogarithms connected to exponential series. City sizes, word frequencies, and wealth distributions often approximately follow Zipf's law. Self-organized criticality produces power law distributions of avalanche sizes, contrasting with exponential distributions seen in subcritical and supercritical regimes. The Sampao model in related systems exhibits scale-free behavior without tuning parameters, a phenomenon distinct from exponential systems. Phase transitions in statistical mechanics separate exponential from algebraic decay of correlations. Below critical temperature, correlations may decay exponentially with separation, while at model criticality, power law decay emerges. The correlation length diverges at the critical point, transitioning from finite exponential scale to infinite algebraic scale. The Ising model on regular lattices has partition function involving exponential sums over spin configurations. At low temperature, order persists with exponential suppression of defects, while high temperature exhibits exponential decay of correlations. The critical point separates these regimes. Potts models generalize Ising to more than 2 states per site, maintaining exponential Boltzmann weights in the partition function. The Q-state Potts model for various Q values shows first-order or second-order phase transitions, depending on dimensionality and Q. Percolation on infinite lattices exhibits exponential cluster size decay, below the critical probability and power law decay exactly at criticality. The correlation length diverges as the critical point approaches, with exponential form in the off-critical regime. Epidemic models like compartmental models show exponential growth when the basic reproduction number exceeds 1, with infected population initially growing as e raised to time times the quantity R0 minus 2, 1 times recovery rate. Intervention strategies aim to reduce R0 below 1, inducing exponential decay. Tumor growth models often assume exponential proliferation in early stages, with von Pertz or von Bertalanffy modifications, introducing saturation as tumors enlarge. The transition from exponential to bounded growth reflects nutrient limitations and spatial constraints. Bacterial colony growth follows exponential patterns when nutrients remain plentiful, with population doubling at regular intervals. The doubling time relates to growth rate through natural logarithm of 2 divided by rate, connecting exponential dynamics to observable quantities. Forest fires spread exponentially when wind and fuel conditions favor propagation, with burned area potentially growing as e raised to growth rate times time. Fire breaks and suppression efforts aim to break exponential spread before uncontrollable conflagration develops. Economic bubbles exhibit exponential price growth disconnected from fundamental values. Driven by speculation and momentum trading, the exponential trajectory becomes unsustainable, inevitably culminating in crashes where prices collapse, sometimes exponentially in the opposite direction. Network effects in technology platforms can generate exponential user growth, when each user attracts multiple new users. Metcalfe's law suggests network value grows quadratically with user count. The user acquisition itself may follow exponential dynamics during rapid adoption phases. Viral marketing campaigns leverage exponential sharing, where each recipient forwards content to multiple others. The effective reproduction number, analogous to epidemiology, determines whether campaigns fizzle or explode exponentially across social networks. Moore's law, describing exponential growth in transistor density over time, held remarkably for decades. Doubling every 18 to 24 months corresponds to exponential increase, with specific growth rate, though physical limits eventually constrain continuation. DNA amplification via polymerase chain reaction follows exponential dynamics, with each thermal cycle ideally doubling template count. After n cycles, the initial template multiplies by 2 to the n, enabling detection of minute quantities through exponential amplification. Phylogenetic trees can exhibit exponential branching when speciation outpaces extinction. Biodiversity through geological time shows periods of exponential radiation, followed by extinctions, creating punctuated patterns in the fossil record. Carbon dating uses exponential decay of carbon-14, with half-life approximately 5,730 years. Measuring the ratio of carbon-14 to carbon-12 and applying exponential decay formula allows age estimation for organic materials up to tens of thousands of years old. Uranium-lead dating of rocks exploits exponential decay chains involving multiple isotopes. Concordia diagrams plot different decay series, with intersections revealing formation, ages through exponential relationships, spanning billions of years. Cosmological redshift stretches light wavelengths exponentially during inflation, with photon wavelength growing proportional to scale factor. Observing distant galaxies provides information about expansion history through exponential stretching of radiation. Baryon acoustic oscillations in cosmic microwave background exhibit characteristic scale determined by sound horizon at recombination. Though not purely exponential, the analysis involves Fourier transforms and exponential kernels, connect real space correlations to power spectra. Structure formation in the universe begins with exponential growth of density perturbations during matter-dominated era. Linear perturbation theory predicts exponential growth proportional to scale factor, breaking down when overdensities become nonlinear and collapse into bound structures. Dark energy's equation of state parameter determines expansion dynamics, with cosmological constant leading to exponential de Sitter expansion. Measuring acceleration constrains dark energy properties through fitting exponential and modified exponential models to supernova distance redshift relations. Gravitational wave strain from binary inspirals grows as systems orbit faster approaching merger, with frequency evolution involving exponential terms in post-Newtonian expansions. Waveform templates incorporate exponential phase evolution for matched filtering in detector data. Pulsar timing arrays detect gravitational waves through correlated timing residuals, with sensitivity depending on observation duration and pulsar stability. Exponential gravitational wave backgrounds for supermassive black hole binaries imprint exponential correlation patterns between pulsars. Primordial gravitational waves from inflation carry information about exponential expansion era, with tensor to scalar ratio constraining inflationary energy scale. Detection would provide direct evidence for exponential accelerated expansion in the early universe. The exponential function threads through virtually every domain of mathematics and science, appearing wherever growth compounds upon itself, or decay proceeds proportionally to remaining quantity. Its ubiquity stems from the fundamental property that the derivative equals the function itself, creating processes that accelerate or decelerate in direct proportion to current state. From the smallest quantum fluctuations to the largest cosmic structures, from fastest chemical reactions to slowest geologic processes, exponential mathematics describes phenomena spanning all scales and domains. The function's elegant simplicity belies profound complexity in its applications. Understanding exponential behavior proves essential for predicting outcomes, managing risks, and recognizing when intuition fails in the face of compounding dynamics. Linear thinking stumbles when confronted with exponential realities, whether underestimating pandemic spread, misunderstanding investment returns, or failing to grasp technological acceleration. Exponentials remind us that small differences in rates create enormous differences in outcomes given sufficient time. A process growing at 3% annually versus 5% seems negligibly different in the moment, but after decades the gap widens dramatically through relentless compounding. This sensitivity to parameters makes exponential systems both powerful and fragile, capable of remarkable growth, but vulnerable to slight changes in conditions. The asymptotic behavior on both ends of the exponential curve illustrates contrasting infinities. Leftward toward negative infinity, the function approaches zero without ever touching, infinitely close yet always separated by some small positive distance. Rightward toward positive infinity, the function explodes beyond all bounds, growing faster than any polynomial, faster than any fixed rate, accelerating toward heights that exceed imagination. Between these extremes lies the realm of human experience, where exponential phenomena manifest in recognizable ways before escaping into abstraction. We witness exponential effects in limited windows, catching glimpses of growth or decay before saturation, depletion, or intervention, disrupts pure exponential evolution. Real systems incorporate feedback, constraints, and complications that modify ideal exponential behavior, yet the underlying mathematics provides essential foundation for understanding actual dynamics. The exponential function represents one of humanity's most important mathematical discoveries, a tool for comprehending change, predicting futures, and navigating a world where compounding effects dominate outcomes. Its study reveals deep connections between apparently disparate phenomena, unified through shared mathematical structure. Whether calculating investment returns, modeling disease spread, analyzing quantum mechanics, or pondering cosmic expansion, the exponential function illuminates the mathematics of self-referential change. The landscape of exponential growth has carried us through forests of doubling and forests of consequence. But there exists a realm we have not yet fully entered. It is the place where exponentials meet their inverse, where growth curves toward infinity, while other curves descend toward zero. This is the territory of exponential decay, and it holds within it some of the most whispered truths about how the world actually works. Think first about what it means to have something that grows exponentially. You began with some quantity. You multiply it by a constant number. Then you multiply the result by that same constant again, and again, the constant we call the base, and each multiplication is another step forward in time. If that base is 2, your quantity doubles with each step. If it is 3, your quantity triples. The larger the base, the faster the climb toward infinity. Now imagine the inverse of this process. Instead of multiplying by something greater than 1, you multiply by something less than 1. Instead of growth, you have decay. Instead of expansion, you have contraction. The mathematics looks almost identical, but the direction is reversed, and this reversal changes everything about how the pattern behaves. Let us work through this slowly. Suppose you have 100 units of something. Perhaps it is a radioactive substance. Perhaps it is the value of currency. Perhaps it is the concentration of a drug in your bloodstream. At the beginning of your measurement, you have exactly 100 units. Time passes. You decide that in 1 unit of time, some proportion of what you have will disappear or transform. Maybe half of it goes away. You are left with 50 units. Time passes again. Half of what remains disappears. You are left with 25 units. Time passes a third time. 50% of 25 is 12.5. You can see how this unfolds. Yes? Each step takes you to a value that is closer to 0, but never quite reaches. The equation that describes this is something like the following. Your final amount equals your starting amount multiplied by the decay constant raised to the power of time. The decay constant is a number between 0 and 1. The power increases with each unit of time that passes. The larger the exponent, the smaller the overall result becomes, because you are multiplying by a fraction again and again. This relationship appears everywhere in nature, and understanding it changes how you perceive patterns you have witnessed your entire life. Consider what happens when something radioactive begins to break down. Uranium-238 decays into lead over billions of years. The amount of uranium present today is not calculated by asking how much there was yesterday and subtracting a fixed amount. If that were true, then after a certain number of days, the uranium would simply run out, like pouring water from a cup, until the cup is empty. Instead, the uranium decays exponentially, meaning that in any given period of time, the fixed percentage of what remains will transform into something else. This is why carbon-14 dating works. Living organisms maintain a certain proportion of carbon-14 relative to carbon-12, because they exchange carbon with the atmosphere. When the organism dies, no new carbon comes in, and the carbon-14 that exists begins to decay. By measuring how much carbon-14 remains, and comparing it to how much should be there initially, scientists can calculate how long ago the organism stopped breathing. The equation underlying this grows from a principle called the half-life. This is the amount of time required for any quantity to reduce to exactly half its previous value. Strontium-90 has a half-life of about 29 years. This means that if you have 1 kilogram of strontium-90 today, in 29 years, you will have half a kilogram. In 58 years, you will have a quarter kilogram. In 87 years, you will have an eighth. The quantity shrinks by half with each passage of a half-life. So after in half-lives, you have your original amount multiplied by 1/2 raised to the power n. This principle extends beyond radioactivity. Medications taken into the bloodstream follow similar patterns. When you take a dose of medicine, it enters your system and begins to work. Over time, your body metabolizes it, converts it, or excretes it. The half-life of the medication tells you how long it takes for your body to eliminate half of what you took. Ibuprofen has a half-life of about 2 hours. If you take 400 milligrams, after 2 hours, your body has processed half of it, leaving 200 milligrams circulating in your system. This is why some medications must be taken multiple times per day. Without redosing, the amount in your system decays exponentially toward 0, and eventually the therapeutic effect diminishes. The same pattern governs how light passes through certain materials. If you have a window of glass, some light passes through while some is absorbed or reflected. The thicker the glass, the less light emerges on the other side. The relationship is not linear. You do not lose a fixed amount of light with each additional thickness unit. Instead, you lose a fixed percentage. Double the thickness, and the amount of light that passes through does not decrease by double, but by the square of the decay factor. This is captured in an expression sometimes called the Lambert-Beer law. which states that the intensity of light emerging from a material is equal to the initial intensity multiplied by the decay constant, raised to the power of the distance the light has traveled through the material. These observations cluster around a single mathematical truth. Exponential decay emerges whenever the rate of change is proportional to the current value. In other words, the more of something you have, the faster it disappears, but only a percentage. 10 grams of a substance decays faster, in absolute terms, than 1 gram of the same substance, but both lose the same percentage per unit time. This principle creates a remarkable symmetry with exponential growth. In growth, we ask, if something doubles every few years, how long until we have 1 billion units? In decay, we ask, if something halves every few decades, how long until nearly all of it is gone? The mathematics responds with the same framework, just with different numbers plugged into different places. Let us think about the geometry of these curves. An exponential growth curve begins slowly, nearly flat, almost unnoticeable, but it accelerates as it rises, becoming steeper and steeper, until the slope seems nearly vertical. The curve never actually stops curving. Even when it reaches enormous heights, it continues to accelerate. This is the shape of disaster, of surprise, of things spinning out of control. The exponential decay curve tells a different story visually. It begins at your starting point and falls steeply at first. The slope is negative and pronounced. But as the curve descends, the steepness decreases. The rate of change slows down. The curve approaches zero, but never touches it, asymptotically reaching toward a baseline it will never quite attain. This is the shape of healing, of forgetting, of things fading away. Both curves, despite their opposite directions, share a fundamental property. They bend in consistent ways relative to their own growth or decay rate. This consistency is what makes exponential processes recognizable across such different domains. There is something particularly important about the relationship between growth and decay in the context of continuous change. When something grows or decays continuously, rather than in discrete steps, we find ourselves in the territory of something called differential equations. These are mathematical statements about how quickly something is changing at any given time. Consider the simplest case. The rate of change of a quantity is proportional to the quantity itself. If we call the quantity y and time t, we might write that the derivative of y with respect to t equals some constant times y itself. This is the fundamental differential equation for exponential processes. The beauty of this equation is that it has a solution, a formula that tells us exactly what y equals at any time t. That solution involves the mathematical constant called e, approximately 2.71828. The constant e is one of the most important numbers in mathematics, rivaling pi in its significance. It emerges naturally whenever you have exponential growth or decay. If something grows or decays continuously, and the rate of change at any moment is proportional to the current value, then the solution involves e. Specifically, the quantity at time t equals the initial quantity multiplied by e raised to the power of a growth rate, constant times t. If the growth rate is positive, the quantity grows toward infinity. If it is negative, the quantity decays toward zero. The number e has a particular definition worth understanding. Imagine you start with $1. A bank offers you interest compounded every year at a rate of 100%. After 1 year, you have $2. Your original dollar plus $1 in interest. Now imagine that instead of compounding once per year, the bank compounds the interest twice per year, at 50% each time. First half year, you earn interest on $1, getting 50 cents. Second half year, you earn interest on $1, 50 cents, getting 75 cents. You end with $2.25. The more frequently you compound, the higher the final amount becomes. If you compound quarterly, you get about $2.44. If you compound daily, you get about $2.71. As you increase the frequency toward infinity, the amount approaches a limit, and that limit is e dollars. This is not merely a mathematical curiosity. It captures something profound about how growth works when you have interest on interest, or growth on growth, compounded infinitely often. It appears in the equation for radioactive decay, in the spread of disease through populations, in the cooling of hot objects in cool environments, in the charging and discharging of electrical capacitors and inductors, in the absorption of light through materials, and in countless other natural phenomena. When we write that a quantity decays exponentially with a half-life of h, we can express this using e as well. The quantity at time t equals the initial quantity, multiplied by e raised to the power of minus t divided by the half-life constant. The presence of the negative sign before the time tells us we are dealing with decay, rather than growth. As time increases, the exponent becomes more negative, and e raised to a more negative power grows smaller and smaller. Understanding exponential decay has profound implications for how we manage things that must eventually be cleaned up or processed. Suppose a pollutant enters a river. The river naturally processes the pollutant through chemical breakdown and settling, removing a certain percentage each day. Environmental scientists can predict how long the pollutant will persist in harmful concentrations. If the decay rate is high, the river recovers quickly. If the decay rate is low, the pollutant lingers dangerously. Adding more pollutant does not slow the percentage removal rate, but it does mean the pollutant takes longer to reach safe concentrations. This has led to an important principle in environmental management. If you want to protect an environment that naturally clears certain pollutants, you may be better served by reducing the rate at which pollutants enter rather than building expensive systems to filter them out directly. If a river can naturally decay 80% of a pollutant per month, then adding less pollutant means it reaches safe levels sooner, even without intervention. Conversely, adding a large amount of pollutant takes longer to decay, even with the same 90% removal rate per month. The mathematics becomes particularly interesting when exponential decay is paired with continuous input. Imagine a reservoir with a drain at the bottom. Water flows in at a constant rate. Water also leaks out through the drain at a rate proportional to the current amount of water in the reservoir. The more water there is, the higher the pressure, and the faster it leaks out. Eventually the system reaches a balance where the rate of water coming in equals the rate going out. At this equilibrium, the amount of water in the reservoir remains stable. What is the amount at equilibrium? It equals the inflow rate divided by the decay rate constant. This relationship is remarkably robust. No matter what the initial condition, the water level will approach this equilibrium value, approaching it exponentially. If you start with an empty reservoir, the water level rises exponentially toward the equilibrium. If you start with an overflowing reservoir, the water level falls exponentially toward the equilibrium. The trajectory changes, but the destination is the same. This principle applies to many systems. A room with heating and cooling will reach a steady temperature where the heat entering equals the heat leaving through windows and walls. A person taking a continuous dose of medication will reach a steady concentration in the bloodstream, where the drug entering equals the drug being metabolized and excreted. A business with constant revenue and constant percentage losses will reach a steady capital amount where income equals losses. In each case, the exponential decay of the excess or deficit drives the system towards equilibrium. There is a particular time constant that characterizes how quickly this approach happens. It is the time required for the excess to decay to about 36% of its initial value. More technically, it is 1 divided by the decay rate constant. If the decay constant is large, the time constant is small, meaning the system equilibrates quickly. If the decay constant is small, equilibration takes a long time. This time constant appears repeatedly in engineering and biology. Engineers designing systems need to know how quickly a system responds to disturbances. Biologists studying drug dosing need to know how quickly medicine reaches and leaves the system. There is another perspective on exponential decay worth exploring, one based on probability. Imagine you have a large population of particles or atoms, each of which has a certain probability of decaying in each tiny interval of time. The probability is the same for each particle, and does not change over time. Even though individual particles decay randomly and unpredictably, the population as a whole decays exponentially. This is a remarkable statistical fact. Randomness at the microscopic level produces determinism at the macroscopic level. This insight explains why exponential decay appears so universally. It does not require a mechanism that says half the atoms must decay by time h. It only requires that each atom has some probability per unit time of decaying. Given enough atoms, the laws of probability guarantee that the population decays exponentially with a predictable half-life. The randomness averages out. This principle has practical implications. A single atom of uranium might decay this second, or might persist for millions of years. You cannot predict which, but if you have a macroscopic sample containing trillions of uranium atoms, you can predict almost precisely how many will have decayed in any given time interval. The greater the sample size, the more predictable the decay. This is why radioactive dating works despite the fundamental randomness of individual decay. The vents. The bridge between probability and exponential decay runs even deeper. If you ask the question of how long you must wait until a randomly decaying particle finally decays, the answer follows what is called an exponential distribution. The probability that the particle survives for time, t or longer, equals e raised to the negative power of the decay rate times t. The probability that it decays within the next tiny interval is proportional to the current number of particles still around. This self-similar property, where the future evolution depends only on the current state and not on how you reach that state, is called the memoryless property, and it uniquely characterizes the exponential distribution. There are many practical scenarios where this matters. If you are waiting for a bus that arrives randomly, your expected wait time does not decrease because you have already waited 10 minutes. From the perspective of the bus, the fact that you have been waiting does not make you more likely to have a bus arrive in the next minute. Your expected remaining wait time is the same as it always was. This can be psychologically surprising, but it is mathematically necessary if the buses arrive according to a truly random process. Conversely, if you know that a bus arrives approximately every 15 minutes on a fixed schedule, and you arrive at a random time, you expect to wait about 7.5 minutes on average. The system has memory of its schedule. The constant e appears in the exponential distribution formula, as it does in nearly all exponential formulas. This points to a deep mathematical truth. E is the natural base for expressing growth and decay. When you use e as the base, the derivative of e to the power of t equals e to the power of t itself. This self-similarity, where the function equals its own rate of change, makes e special. It is why it appears in solutions to differential equations governing exponential growth and decay. In the realm of complex systems, exponential decay often represents the return to equilibrium after a disturbance. If you pluck a guitar string, it vibrates at a particular frequency, but the amplitude of vibration decays exponentially due to friction and air resistance. The time for the vibration to decay to a whisper depends on the material properties and environmental factors, all captured in a single decay constant. Similarly, if you push a pendulum from its resting position, it swings back and forth with gradually diminishing amplitude, driven toward equilibrium by friction and gravity. The envelope of the motion decays exponentially. These damped oscillations are ubiquitous in engineering. Shock absorbers in vehicles use this principle to bring the vehicle to stable height after a bump. Electrical circuits use damping to prevent oscillations that would interfere with the desired signal. Building materials are designed to have appropriate damping, so that vibrations from earthquakes or wind dissipate, rather than build up to destructive levels. The decay constant determines the quality of the damping. Too much damping makes the system slow to respond. Too little damping allows oscillations to persist too long. Engineers seek the Goldilocks zone, where the response is appropriately fast and stable. When we zoom out to consider exponential decay in biological and ecological contexts, new patterns emerge. The concentration of a hormone in the blood decays exponentially after it is released. The population of predators decays exponentially after their prey population collapses. The activity of an enzyme decays exponentially as it is degraded by cellular machinery. The brightness of bioluminescent creatures decays exponentially as their chemical reserves deplete. Life seems shot through with exponential decay. This makes sense from an evolutionary perspective. Natural selection has favored mechanisms that respond to changes in a way proportional to the current level. A predator population that shrinks by a fixed percentage when prey are scarce adapts better than one that loses a fixed number of individuals regardless of population size. A hormone system that produces a declining response proportional to current concentration adapts better than one that declines rigidly. The mechanisms of decay in biology tend to be percentage-based, rather than fixed amount-based. And percentage-based decay is exponential decay. There is also something about exponential decay that feels psychologically natural to humans, though we often misunderstand it. When you experience something emotionally difficult, you might expect that you will forget it by a certain date. But forgetting is often exponential. Early on you think about the event constantly, and it weighs heavily. Gradually you think about it less. The intensity of the memory decays. But it does not reach zero. A sudden trigger can bring it all back vividly. The memory traces never entirely vanish, but they fade exponentially toward a residual level. Learning exhibits similar patterns. When you learn a new fact, you remember it easily immediately after learning. As time passes and you do not review the material, your ability to recall it decays exponentially. This is why spaced repetition learning systems work so well. By reviewing the material just as it is about to be forgotten, you reset the decay timer. Frequent review keeps the material from reaching the exponential decay threshold, where it becomes effectively lost. This is why cramming the night before an exam can work temporarily, but does not produce long-term retention. The exponential decay of memory will erase what you memorize without reinforcement. In the context of forgetting, there is an interesting mathematical relationship. The amount you remember of something you learned equals the time since learning raised to the power of a negative exponent. This is called the power law of forgetting, and it is different from exponential decay, though both describe forgetting over time. The power law relationship suggests that you remember very little after a long time, but you lose a lot early on. The transition is smoother than exponential decay. Different cognitive systems may follow different forgetting laws depending on the mechanisms involved. When we turn to ecosystems, the exponential decay governs how ecological disturbances recover. If a forest is partially cleared by a storm, the tree population does not recover linearly, sprouting a fixed number of new trees each year. Instead, recovery is often exponential, with the growth rate depending on the capacity of the remaining ecosystem to regenerate. Young trees grow faster, increasing the total mass of vegetation. More vegetation supports more wildlife. More wildlife supports more vegetation. The system accelerates towards recovery, though the trajectory is exponential rather than linear. The time constant for recovery depends on species longevity and reproductive rates. Similarly, when a population of organisms is depleted by hunting or disease, then hunting or disease pressure is removed. The population does not recover at a steady linear rate. Instead, recovery is often exponential in the early stages, when every individual has abundant resources and few competitors. As the population grows and resources become scarcer, the growth rate slows. Eventually, the population reaches a carrying capacity where birth rate equals death rate, and further growth stops. The shape of this curve is called logistic growth, and it is exponential growth constrained by a limit. The mathematics shows that the population approaches its carrying capacity exponentially, converging from below if the population started small, or converging from above if the population started large. There is profound beauty in how exponential decay appears when we examine things that are broken or damaged. Suppose you have a system that works through the cooperation of many components, and each component has some probability of failing per unit time. The probability that the system continues to work depends on whether all components work or whether it has some redundancy. The simplest case, where every component is required, means the system fails when the first component fails. If each component has an exponential lifetime distribution, then the system lifetime follows an exponential distribution, and many individual components combine to create a system reliability that decays exponentially with time. This is why critical systems like aircraft and power plants have redundancy and maintenance schedules. A single pump might fail exponentially, but 2 pumps with automatic switching provides reliability with a much longer time constant. 3 pumps with voting logic provides even greater reliability. The mathematics shows exactly how much redundancy you need to achieve a desired reliability level. Similarly, preventive maintenance programs replace components before they reach high failure probability, essentially resetting the failure clock. A component that is new has low failure probability. As it ages, the probability increases. Replacing old components with new ones before they reach high failure probability keeps the overall system failure rate low. The exponential failure law has profound implications for how long systems last and how to manage them optimally. If a system follows exponential failure patterns, the average time before failure is 1, divided by the failure rate constant. If you want to double that lifetime, you might try to halve the failure rate through better materials or design, but sometimes the more economical approach is to add redundancy or to implement preventive maintenance. The mathematics of exponential processes helps optimize these decisions. When we examine the cooling of heated objects, we again encounter exponential decay. A cup of hot tea cools down through heat loss to the environment. Rate of heat loss is proportional to the difference between the tea temperature and the room temperature. This proportionality creates an exponential decay of the temperature difference. The tea temperature approaches the room temperature exponentially. The time constant for cooling depends on the cup material, the surface area, and properties of the surrounding air. A thin ceramic cup cools faster than a thick ceramic cup. A cup in still air cools slower than a cup in moving air. The mathematics allows us to predict exactly how fast cooling will occur given these parameters. The principle extends beyond temperature. A hot wire in a gas cools rapidly. A warm hand in cold water loses heat quickly. A room with an open window cools faster than a sealed room. In each case, the cold environment or medium does not instantly equalize the temperature, but rather drives exponential decay of the temperature difference. The same exponential approach to equilibrium occurs whenever there is a loss mechanism proportional to the driving force. In the electrical domain, the charging and discharging of capacitors follows exponential laws. The capacitor holds electrical charge on its plates. When you connect a charged capacitor to a resistor, the charge leaks away exponentially. The time constant for discharge equals the resistance times the capacitance, a simple product of 2 component properties. Increase the resistance and discharge slows. Increase the capacitance and discharge slows. The product of these two quantities determines how quickly the energy stored in the capacitor dissipates. When you connect a discharged capacitor to a voltage source through a resistor, the opposite occurs. The capacitor charges exponentially, approaching the source voltage. The same time constant governs charging and discharging. This time constant appears throughout electronic circuits, determining how quickly circuits can respond to changes. A circuit with a large time constant responds slowly to input changes. A circuit with a small time constant responds quickly. Designers choose components to achieve the desired time constant for the application. There is something contemplative about exponential decay that might appeal to how humans naturally think about some processes. The idea that something gradually fades, losing a percentage of what remains at each step, rather than falling off a cliff or disappearing in a step function, feels closer to how we experience many changes in life. Relationships do not typically end instantly, but rather dissolve exponentially through accumulated neglect. Skills do not vanish when unused, but rather fade exponentially through forgetting. Opportunities do not disappear entirely, but become exponentially less likely, the longer you delay. The exponential model captures the flavor of gradual, proportional loss that characterizes so much of lived experience. The mathematics of exponential decay provides a language for discussing these processes with precision. Instead of saying something slowly fades, you can say it decays with a particular time constant. Instead of saying something eventually goes away, you can say it approaches zero asymptotically. Instead of saying something reaches a balance, you can describe the equilibrium value and the rate at which it is approached. This precision allows for better prediction and planning. In medicine, the concept of exponential decay of drug concentration has led to sophisticated dosing strategies. Instead of taking a medication once a day, you might need to take it twice or 3 times a day, depending on how rapidly your body processes it. The goal is to keep the drug concentration within a therapeutic window, above a minimum effective level and below a maximum safe level. If the drug decays slowly, once daily dosing might be sufficient. If the drug decays quickly, more frequent dosing is needed. For some conditions, doctors use continuous infusion, where medication is dripped slowly into the bloodstream at a rate that exactly balances the decay rate, maintaining constant therapeutic concentration indefinitely. The same principles apply to nutrients and toxins in the body. Vitamin B12 persists in your body for years because your body decays it very slowly. You can go months without eating animal products before B12 deficiency becomes apparent. In contrast, vitamin C is quickly metabolized and excreted. Your body cannot store it, so you need a continuous supply. Too much is simply lost in urine. Toxins like heavy metals accumulate over time because your body decays them slowly. Exposure to small amounts may not cause immediate harm, but over years, the cumulative burden can become dangerous. The time constant for accumulation determines whether a toxin is a problem for short-term exposure or long-term health. When we consider how information decays in technology systems, we again encounter exponential patterns. The signal passing through a long electrical cable experiences attenuation, with the signal strength decaying exponentially with distance. To transmit signals over long distances, you must amplify them periodically. The spacing between amplifiers depends on how rapidly the signal decays. A signal that decays quickly requires amplifiers closer together. This principle applies to both electrical signals in cables and light signals in fiber optic cables. The distance you can transmit without amplification is directly related to the decay constant of the medium. In wireless communication, signals propagate outward from a transmitter and decay exponentially with distance due to spreading and absorption. The received signal strength depends on transmission power, antenna gains, frequency, and the distance between transmitter and receiver. The range of a transmitter is the distance at which the signal becomes too weak to reliably detect, a point determined by exponential decay of the signal as it spreads. Cellular networks and wireless internet routers must be spaced appropriately to maintain coverage, with spacing determined by the exponential decay of signal strength with distance. The principle of exponential decay appears even in how financial assets lose value. A car depreciates, losing a percentage of its value each year, rather than a fixed dollar amount. The older the car, the slower the depreciation, approaching a salvage value asymptotically. A building depreciates similarly, with the value approaching the land value as the structure ages. The time constant for depreciation depends on how quickly the asset becomes obsolete or worn. A technology device might depreciate rapidly as newer models emerge. Real estate might depreciate slowly as the land retains value. The mathematics of depreciation guides decisions about when to replace equipment or invest in maintenance. Looking toward the broader implications of exponential decay, One of the most important applications is in the management of resources that naturally regenerate. A forest naturally regrows if left undisturbed. The rate of regrowth depends on climate, soil, and species mix. If you harvest the forest at a rate equal to or below the natural regrowth rate, the forest is sustainable. If you harvest faster than it grows, the forest shrinks exponentially toward collapse. The mathematics shows that sustainable harvest equals the regrowth rate. Harvest faster and exponential decay towards zero forest area is inevitable. Harvest slower, and the forest area increases exponentially. Only at the matching point does the forest reach a stable size. Fisheries operate under the same principles. Fish populations regrow through reproduction. If you fish at a rate equal to or below the natural population growth rate, the fishery is sustainable. If you fish faster, the population decays toward collapse. The tragedy of the commons occurs because individual fishermen do not bear the full cost of overfishing, profit from catching more fish, while the cost of the depleted fishery is shared among all. This creates an incentive to harvest faster than is sustainable. Mathematics shows the inevitable outcome: exponential decay of the fish population to near zero, at which point fishing becomes uneconomical. The concept of sustainability can be expressed mathematically through exponential decay. A sustainable system reaches an equilibrium, where inflows equal outflows, growth equals harvest, births equal deaths. Perturb the system above equilibrium, and exponential decay back toward equilibrium is driven by scarcity. Perturb it below equilibrium, and exponential decay toward equilibrium is driven by abundance. Only at the equilibrium point is the system stable. Understanding the mathematics of exponential processes is thus understanding the mathematics of sustainability. Human behavior sometimes makes exponential decay seem counterintuitive. After an exhausting day, you expect to feel rested after a night of sleep, and indeed, the fatigue decays exponentially towards zero with sleep. You expect to feel fully recovered, not just mostly recovered. But full recovery would require infinite time, as fatigue approaches zero asymptotically, but never quite reaches it. In practice, you reach a point of diminishing returns, where additional sleep provides little additional benefit. The exponential decay means that most of the recovery happens early, with increasingly small increments of benefit from further sleep. This is why an extra hour of sleep provides much more benefit to a very tired person than to a well-rested person. The exponential shape of the decay curve means the steepest part is at the beginning. This has implications for many self-care practices. The first week of exercise provides the largest health benefits, because your baseline fitness is low. Later weeks provide benefits too, but smaller ones as you approach your genetic limit for fitness. Conversely, during the first week without exercise, your fitness decays rapidly. A week of sedentary behavior does more damage to a fit person than to an out-of-shape person in terms of percentage decline. The exponential nature of fitness change means that maintaining fitness requires only moderate effort to prevent decay from accumulating. This is why use it or lose it is a common saying. Fitness decays exponentially without reinforcement. As we contemplate the full landscape of exponential decay, from the atomic realm of radioactivity to the macroscopic realm of celestial decay, and everything in between, we recognize that decay is not a process of sudden collapse or linear decline. Rather, it is a process of proportional reduction, where each unit of time sees a fixed percentage loss rather than a fixed amount. This proportionality creates curves that fall steeply at first, then gradually flatten, approaching a limit asymptotically. These curves are among the most common shapes in nature, appearing wherever systems are driven toward equilibrium or stability. Understanding exponential decay is thus understanding how systems settle, how disturbances dissipate, how noise becomes signal, how disorder becomes order. It is understanding the mathematics of restoration, recovery, and return. The interplay between exponential growth and exponential decay creates the dynamism of the natural world. Populations grow exponentially when resources are abundant, then decay exponentially towards sustainable levels as resources become scarce. Signal grows exponentially from noise by amplification, then decays exponentially back towards noise as transmission distance increases. Energy accumulates in systems through growth, then dissipates through decay. The balance between growth and decay, equilibrium and disturbance, is what creates the rich complexity of the world as we experience it. By understanding exponential decay, we understand one half of the mechanism that drives the dance. Looking at the path we've traced so far, we arrive at something that feels almost inevitable. Exponentials have threaded through everything, sometimes visible, sometimes hiding beneath other structures. Now we turn to face them directly, to see what they reveal when we stop treating them as tools, and start treating them as landscapes worth exploring on their own terms. The exponential function sits at a strange intersection. Its growth incarnate, the mathematical expression of compounding, of things building on themselves. Start with 1, multiply by some base repeatedly, and you get exponential growth. 1 becomes 2, becomes 4, becomes 8. The pattern is relentless, mechanical even, yet it describes so much of what happens in the world. Populations grow exponentially when resources are unlimited. Radioactive decay follows exponential curves downward. Money compounds. Epidemics spread. The pattern appears everywhere we look. But there's something deeper happening. The exponential function isn't just about repeated multiplication. It's the unique function that equals its own derivative, the function that changes at a rate proportional to its current value. This property makes it fundamental to calculus, to differential equations, to any situation where how fast something changes depends on how much of it there is. When we write e raised to x, we're invoking a specific base, the number e, approximately 2.71828. This number appears naturally when we ask what base makes the derivative of the exponential function equal to the function itself. With any other base, say 2 raised to x, the derivative is a constant multiple of the function. Only with base e does that constant equal exactly 1. The number e itself emerges from a limit. Consider the expression 1 plus 1 over n raised to the n power. As n grows, this expression approaches e. When n equals 1, we get 2. When n equals 10, we get about 2.59. When n equals 100, we get about 2.705. The limit as n goes to infinity is e exactly. This limit has a beautiful interpretation. Imagine interest compounding on the loan. If the annual interest rate is 100%, and it compounds once per year, you get 1 plus 1 equals 2 times your original amount. If it compounds twice per year at 50% each time, you get 1 plus 1 half, squared equals 2.25. If it compounds n times per year at 1 over n per period, you get 1 plus 1 over n raised to n. As the compounding becomes continuous, happening every instant rather than at discrete intervals, the growth factor approaches e. So e is the natural base for continuous compounding. It's what you get when growth is perfectly smooth, when changes happen infinitesimally, rather than in chunks. This makes it the right base for modeling continuous processes, which is most of what we actually care about in science and engineering. The function e raised to x has remarkable properties beyond being its own derivative. It's always positive, never crossing 0. As x goes to negative infinity, the function approaches 0 from above. As x goes to positive infinity, it grows without bound. The curve is smooth, increasing everywhere, ending upward in that characteristic exponential curve. We can extend the exponential to complex numbers. What does e raised to I mean, where I is the square root of -1? Euler's formula provides the answer. E raised to I times theta equals cosine theta plus I times sine theta. This connects the exponential function to trigonometry in a profound way. When theta equals pi, we get e raised to I times pi equals cosine pi plus I times sine pi equals -1 plus 0 equals -1. Rearranging gives e raised to I times pi plus 1 equals 0. Euler's identity, often called the most beautiful equation in mathematics. That links 5 fundamental constants, e, I, pi, 1, and 0. This complex exponential rotates around the unit circle in the complex plane. As theta increases, e raised to I times theta traces a circle of radius 1, moving counterclockwise. The exponential function, which seemed purely about growth, becomes about rotation when we pass to complex numbers. For general complex e equals x plus I times y, we have e raised to z equals e raised to x times y equals e raised to x times c raised to I times y equals e raised to x times the quantity cosine y plus I times sine y. The magnitude is e raised to x, depending only on the real part. The phase is y, depending only on the imaginary part. The complex exponential separates growth from rotation. This makes the exponential function the right tool for describing oscillations. The damped oscillation, something vibrating while gradually losing energy, has the form e raised to negative a times t times cosine omega times t, where a is the damping coefficient and omega is the frequency. We can write this using complex exponentials. as the real part of e raised to negative a plus I times omega times t. Differential equations governing oscillating systems naturally involve exponentials. The equation for a harmonic oscillator, d squared x over dt squared plus omega squared x equals 0, has solutions that are sines and cosines, but these are really just combinations of e raised to I times omega times t and e raised to negative I times omega times t, and e raised to negative I times omega times t. The exponential form often makes calculations cleaner. When we add damping, getting d squared x over dt squared plus 2 times b x dn's dt plus omega squared x equals 0, the solutions involve exponentials multiplied by exponentials. If b is less than omega, we get damped oscillations, e raised to negative b times t times cosine square root of omega squared minus b squared times t. If b equals omega, we get critical damping, a pure exponential decay without oscillation. If b is greater than omega, we get overdamping, a sum of two exponentials with different decay rates. All of these behaviors emerge from the fundamental property that exponentials are eigenfunctions of differentiation. When we assume a solution of the form e raised to lambda times t and substitute into the differential equation, we get an algebraic equation for lambda. Solving that algebraic equation tells us which exponentials appear in the solution. This eigenfunction property extends to partial differential equations. The heat equation, describing how temperature diffuses through a material, is dt over dt equals alpha times d squared t over dx squared. Separating variables, assuming t of x and t equals x of times tau of t, we get tau equals e raised to negative alpha times k squared times t, and x is a combination of sines and cosines, with spatial frequency k. The general solution is a sum over all frequencies, each frequency decaying exponentially in time, at a rate proportional to its square. High frequencies die out quickly. Low frequencies persist. Eventually everything smooths to a uniform temperature. The wave equation, d squared u over dt squared equals c squared times d squared u over dx squared, has solutions that combine exponentials differently. We get u of x, then t, proportional to e raised to I times k, times x, times e raised to plus or minus I, times omega times t, or omega equals c times k. These are traveling waves, patterns moving through space at speed c. Both equations, heat and wave, have exponentials at their core. The difference is whether time appears linearly or quadratically in the equation. Linear time gives oscillation and propagation. Quadratic time gives diffusion and decay. Now consider what happens when we compose exponentials with themselves. The function e raised to x is one such composition. We could also consider e raised to x is one such composition, or x, or any more variations. Each creates different behavior. The function e raised to x grows faster than any polynomial, faster than any single exponential, faster than anything we can easily imagine. When x equals 0, the value is e raised to 1, which is e. When x equals 1, the value is e raised to e, roughly 15.15. When x equals 2, the value is e raised to e squared, roughly 17,000. When x equals 3, we're already in the millions. This is sometimes called double exponential growth or tetration of order 2. It makes ordinary exponential growth look almost linear by comparison. In practical terms, such functions rarely appear in physics, because nothing in the real world can grow that fast for long. But they appear in complexity theory, in certain combinatorial problems, in places where we're counting abstract possibilities, rather than physical quantities. The derivative of e raised to x involves the chain rule. We get e raised to x times e raised to x. The inner function e raised to x has derivative e raised to x. The outer function e raised to u has derivative e raised to u. To multiply them together, the result is e raised to x times e raised to x, which we can also write as e raised to the quantity x plus e raisedness. This derivative is itself growing double exponentially. It grows even faster than the original function in a certain sense. The ratio of the derivative to the function is e raised to x, which is increasing exponentially. This means the function is accelerating exponentially. Not only is it growing, but the rate at which it's growing is itself growing exponentially. Higher derivatives compound this effect. Second derivative is e raised to x times e raised to x, times the quantity 1 plus e raised to x. The third derivative involves more terms, all growing at comparable rates. Each differentiation multiplies by another factor, that's roughly e raised to x, for large x. Integrating e raised to x, as we've noted before, produces no elementary closed form. The antiderivative must exist as a matter of calculus, but cannot be expressed using familiar functions. We can write it as the integral from 0 to x of e raised to t with respect to t, which is correct, but doesn't simplify further. We could expand as a Taylor series and integrate term by term. The series for e raised to x starts with e raised to 1 plus e raised to 1 times the quantity x minus 1 plus e raised to 1 times the quantity x minus 1 squared over 2 factorial plus e raised to 1 times the quantity 2 plus 1 times the quantity x minus 1 cubed over 3 factorial. The pattern continues growing more complex. Integrating term by term gives us a series for the antiderivative. The constant term e raised to 1 integrates to e raised to 1 times x. The linear term e raised to 1 times the quantity x minus 1 integrates to e raised to 1 times the quantity x minus 1 squared over 2. Each term integrates straightforwardly as a polynomial in x minus 1. This series representation is valid in some neighborhood of x equals 1. It converges for x near 1, though how near depends on the function's behavior. For large x, the series doesn't help much because the convergence is too slow. We'd need other methods, asymptotic expansions or numerical integration, to evaluate the antiderivative far from the expansion point. The broader lesson is that composition creates complexity. The exponential function by itself is tractable, well understood, easy to work with, but nesting exponentials, even once, produces something qualitatively more difficult. Twice tripling exponentials to create e raised to x makes things even worse. There's a hierarchy of growth rates. Polynomials grow according to their degree. Linear functions grow slowest, then quadratic, cubic, and so on. Exponentials grow faster than any polynomial. Double exponentials grow faster than any single exponential. Triple exponentials faster still. This hierarchy continues indefinitely. At the other end, inverse functions decay instead of grow. The natural logarithm, the inverse of the exponential, grows slower than any positive power of x. The function log x grows slower still. These ultra-slow growing functions appear in complexity theory, measuring how efficiently certain algorithms perform. Between growth and decay sits a balance point. Functions that grow exactly fast enough to stay bounded, but not so slow as to go to zero. These are the borderline cases, often the most interesting. They include things like x raised to the 1 over x power, which peaks at x equals e, and then slowly decreases. The exponential function's domain and range are worth examining closely. For real numbers, the domain is all real x, and the range is all positive real numbers. Every positive number can be expressed as e raised to something. If you want to get 10, you raise e to the natural log of 10, which is about 2.303. If you want 1/2, you raise e to negative natural log of 2, which is about negative 0.693. The natural logarithm is the inverse function of the exponential. It undoes exponentiation. If y equals e raised to x, then x equals natural log of y. The logarithm takes positive numbers and returns their exponents. It converts multiplication into addition. The natural log of a times b equals natural log of a plus natural log of b. This property makes logarithms useful for understanding multiplicative processes. The graph of natural log of x is the reflection of e raised to x across the line y equals x. It passes through the point 1, 0, since e raised to 0 equals 1. It increases everywhere but very slowly. As x approaches infinity, natural log of x approaches infinity too, but much more gradually than x itself grows. The derivative of natural log of x is 1 over x. This inverse relationship, where the exponential's derivative is itself, and the logarithm's derivative is 1 over the input, reflects their inverse nature. Composing them in either order gives the identity function, at least when domains are respected. For complex numbers, both functions become multi-valued, or require branch cuts. The exponential e raised to z is single-valued for complex z, taking every non-zero complex value infinitely many times, due to the periodicity in the imaginary direction. But the logarithm of a complex number is not unique. If z equals e raised to w, then z also equals e raised to w plus 2 pi I times n, for any integer n. We choose a principal branch of the logarithm, typically taking the imaginary part, between negative pi and pi. This makes log single-valued on the complex plane, minus the negative real axis. But crossing that branch cut causes the logarithm to jump discontinuously. This is a general feature of inverse functions in the complex plane. They tend to be multi-valued unless we restrict their domains carefully. The square root has 2 values, the cube root 3 values, the nth root n values. The logarithm has infinitely many values, spaced 2 pi I apart. These multiple values are not errors or ambiguities. They're genuine features of the complex structure. Each value is equally valid mathematically. Which one we use depends on context, on which branch we've chosen to work with. The complex exponential connects to power series in a direct way. We've written e raised to z equals the sum from n equals 0 to infinity of z to the n over n factorial. This series converges for all complex z, making the exponential an entire function, analytic everywhere in the complex plane. The radius of convergence is infinite. No matter how large z gets, the series still converges, because factorials in the denominators grow faster than any polynomial in the numerator. This rapid growth of factorials ensures convergence. Other exponential-type functions have finite radii of convergence. The function 1 over the quantity 1 minus z equals the sum from n equals 0 to infinity of z to the n converges only for the magnitude of z less than 1. This geometric series diverges outside the unit circle. The 1 over 1 minus z is a rational function, not an exponential. Its singularity at z equals 1 prevents it from being entire. The exponential has no singularities anywhere in the finite complex plane. Its only singularity is at infinity, and that's an essential singularity, a point where the function's behavior is maximally wild. Near an essential singularity, an analytic function takes on every complex value, infinitely often, in every neighborhood, with at most one exception. For the exponential, the exception is 0. Every other complex number is achieved infinitely many times near infinity. This is Picard's great theorem, a remarkable result. It says that essential singularities are truly singular, fundamentally different from poles or removable singularities. The function doesn't just blow up, it thrashes around in the complex plane, hitting almost everything infinitely many times. For e raised to z, the behavior is even more extreme. This function also has an essential singularity at infinity, and it too takes on every complex value except 0 infinitely many times near infinity. But because it's a composition of exponentials, its behavior is doubly wild in some sense. The modulus, the absolute value of e raised to z, depends on the real part of e raised to z. If z equals x plus I times y, then e raised to z equals e, placed to x times e raised to I times y, with modulus e raised to x. So e raised to z has modulus e raised to x times cosine y. For fixed x, as y varies, cosine y oscillates between -1 and 1. So e raised to x times cosine y varies between negative e raised to x and e raised to x, meaning the modulus of e raised to e raised z varies between e raised to negative e raised to x and e raised to e raised to x. This is an enormous range once x is even moderately large. When x equals 3, e raised to x is about 20, so the modulus varies between e raised to -20, which is tiny, and e raised to 20, which is huge. The function oscillates wildly in magnitude as we move in the imaginary direction. The phase, the argument of e raised to z, is similarly complex. It depends on the imaginary part of e raised to z, which is e raised to x times sine y. This winds around as y increases, creating spiraling behavior in the complex plane. Visualizing this function requires thinking carefully about what we want to see. We could plot the magnitude as a surface over the complex plane, watching it grow and oscillate. We could use color to represent phase, creating a domain coloring. We could trace curves where the magnitude is constant, or where the phase is constant. Each visualization reveals different aspects. The magnitude plot shows the exponential growth in certain directions, and the oscillation in others. The phase plot shows the winding and spiraling. Together they give a sense of the function's rich structure. But no single picture captures everything. This is a function from 2 real dimensions, the complex plane, to 2 more real dimensions, the complex output. We're trying to visualize 4-dimensional information, which requires choices about what to project or slice or color. One approach is to fix the imaginary part of the input, then plot the output as the real part varies. Or fix the real part, then vary the imaginary part. Or trace the image of various curves in the input plane. Each choice gives partial information. The exponential function's collection to differential equations extends far beyond simple examples. Consider the matrix exponential, defined for square matrices in analogy with the scalar exponential. If A is a matrix, we define e raised to a as the sum from n equals 0 to infinity of a to the n, power over n factorial. This series converges for any matrix, just as the scalar series converges for any complex number. The matrix exponential has properties similar to the scalar exponential. If a and b commute, meaning a times b equals b times a, then e raised to a plus b equals e raised to a times e raised to b. The matrix exponential is the solution to systems of linear differential equations of constant coefficients. If dy over dt equals a times y, or y as a vector and a as a constant, matrix the solution is y of t equals e raised to a times t times y of 0. To compute e raised to a times t, we can diagonalize a if possible, finding matrices p and d such that a equals p times d times b inverse, where d is diagonal. Then a to the n equals p times d to the n times p inverse. And the series for e raised to a becomes e raised to a equals p runs to e times t inverse to c. D is diagonal. Since d is diagonal, e raised to a is just the diagonal matrix with e raised to each diagonal entry of d. This reduces the matrix exponential to scalar exponentials of the eigenvalues. If a can't be diagonalized, we use the Jordan normal form, which is almost diagonal, with ones just above the diagonal in certain places. The exponential of a Jordan block involves not just exponentials, but also polynomials times exponentials. All of this machinery exists to solve differential equations. The abstract structure mirrors the concrete calculations we do for scalar equations. Eigenvalues of the matrix play the role of the constants lambda in scalar equations. Eigenvectors give the direction of exponential growth or decay. In physics, these matrix exponentials describe quantum time evolution. Schrödinger equation, I times d psi over dt equals h times psi, as solution psi of t equals e raised to negative I times h times t times psi of 0, where h is the Hamiltonian operator. For finite-dimensional systems, this is a matrix exponential. The Hamiltonian's eigenvalues are the energy levels. The eigenvectors are the stationary states. The time evolution operator e raised to negative I times h times t rotates the state vector in Hilbert space, creating the dynamics of quantum mechanics. So exponentials are not just mathematical abstractions. They describe how systems evolve in time, how waves propagate through space, how quantum states interfere and decohere. They're the functions of change, of dynamics, of becoming. Let's return to growth rates and comparisons. We've said exponentials grow faster than polynomials. More precisely, for any polynomial p of x and any exponential e raised to a times x with a positive, the ratio e raised to a times x over p of x goes to infinity as x goes to infinity. This means that eventually, no matter how large the degree of the polynomial or how large its coefficients, the exponential overtakes it and grows faster. The polynomial might leave for mean a while if it has huge coefficients or very high degree, but asymptotically exponential wins. Similarly, logarithms grow slower than any positive power. The ratio natural log of x over x raised to epsilon goes to 0, as x goes to infinity, for any epsilon greater than 0, no matter how small. Logarithms grow, but barely, compared to power functions. Between polynomials and exponentials sits a rich landscape of intermediate growth rates. Functions like x raised to natural log of x, which is also e raised to natural log of x, times natural log of x, grow faster than any polynomial, but slower than any exponential. These superpolynomial but sub-exponential functions appear in complexity theory, particularly in factoring algorithms. There are even finer distinctions. The function e raised to the square root of natural log of x grows faster than any polynomial, but slower than any exponential. It's in a class called sub-exponential. Algorithms with this running time are faster than exponential but not polynomial. The hierarchy of growth rates is densely ordered. Between any two growth rates, we can find infinitely many intermediate ones. This makes classification tricky. Resort to asymptotic notation, saying a function is big O of another if it grows at most as fast, or big omega if at least as fast, or big theta if they grow at the same rate up to constant factors. These notations let us compare algorithms and functions without getting bogged down in exact formulas. We care about long-term behavior, about what happens as inputs get large, not about small inputs where everything is fast anyway. Exponentials also appear in probability and statistics. The normal distribution, the bell curve, has probability density proportional to e raised to negative f squared over 2. This exponential of a quadratic creates the characteristic shape, peaking at 0 and falling off rapidly in both directions. The normal distribution is ubiquitous because of the central limit theorem. Sums of many independent random variables, regardless of their individual distributions, tend toward normality as the number of terms increases. The exponential function emerges from this limiting process. Other distributions involve exponentials too. The exponential distribution itself, used to model waiting times, has density a times e raised to negative a times x for a's positive. The Poisson distribution, counting rare events, has probabilities e raised to negative lambda times lambda to the k over k factorial. Exponentials and their relatives pervade probabilistic models. In information theory, the exponential appears in the definition of entropy and encoding theorems. If a message has probability p of occurring, its information content is negative natural log of p. Summing over all messages weighted by their probabilities gives entropy. The connection to exponentials is that entropy measures the exponent in the number of typical sequences. If we have n independent uses of a channel with entropy h, there are roughly 2 raised to n times h typical sequences. The exponential function converts entropy to account. Maximum entropy distributions, those that make the fewest assumptions given constraints, often involve exponentials. If we know only the mean, the maximum entropy distribution is exponential. If we know the mean and variance, it's normal. These distributions maximize randomness subject to what we know. Shannon's noisy channel coding theorem says we can communicate reliably at any rate below channel capacity by using exponentially long codes. The probability of error goes to 0, exponentially fast in the code length. The exponentials govern how quickly we can make communication reliable. Now consider the function e raised to negative x. This is a decreasing exponential, approaching 0 as x goes to infinity, and approaching infinity as x goes to negative infinity. It's the mirror image of e raised to x, reflected across the vertical axis. Decreasing exponentials model decay processes. Radioactive decay follows this pattern. If you start with some amount of a radioactive substance, after time t, you have the original amount times e raised to negative lambda times t, where lambda is the decay constant. Half-life is the t when this equals 1/2, which occurs at t equals natural log of 2 over lambda. Cooling also follows exponential decay. Newton's law of cooling says the temperature difference between an object and its surroundings decreases exponentially over time. If T of t is temperature, and T sub s is surrounding temperature, then T of t minus T sub s equals the quantity T of 0 minus T sub s times e raised to negative k times t. Charging and discharging capacitors, drug concentrations in the bloodstream, atmospheric pressure, as a function of altitude all follow exponential patterns, some increasing, some decreasing, all reflecting a fundamental property that the rate of change is proportional to the current amount. The function e raised to negative x squared, without the division by 2, is the unnormalized Gaussian. Its integral from negative infinity to infinity is the square root of pi, a famous result. To normalize it, we divide by this integral, giving 1 over the square root of 2 pi times e raised to negative x squared over 2. This function decays faster than any exponential of x alone, because the exponent grows quadratically rather than linearly. It's sometimes called superexponential decay. By the time x reaches 3 or 4, the value is already negligibly small. Such rapid decay makes the Gaussian convenient for analysis. Almost all the probability mass sits near the center. Tails are negligible. We can truncate integrals at a few standard deviations without significant error. The Gaussian also has the nice property that its Fourier transform is another Gaussian. The transform of e raised to negative x squared is proportional to e raised to negative omega squared over 4. Self-similarity under Fourier transform makes Gaussian special, connecting time and frequency domains in a symmetric way. In quantum mechanics, Gaussian wave packets are the minimum uncertainty states, saturating the Heisenberg uncertainty principle. They're as localized as quantum mechanics allows, balancing position and momentum uncertainties. Multiplying 2 Gaussians gives another Gaussian. Convolving 2 Gaussians gives a Gaussian with variance, equal to the sum of the original variances. These closure properties make Gaussian processes mathematically tractable. But let's return to compositions and nestings. We've discussed e raised to x. What about x raised to x? This is also a super exponential function, though defined differently. For positive x raised to x equals e raised to x times natural log of x. As x increases from 0, x raised to x starts at the limit value 1, which requires some care to define. We take the limit as x approaches 0 from above, let x raised to x equals the limit of e raised to x times natural log of x. As x approaches 0, natural log of x goes to negative infinity, but x times natural log of x goes to 0. So the limit is e raised to 0 equals 1. The function x raised to x decreases slightly from 1, reaching a minimum around x equals e to the negative 1, where the value is about 0.692. Then it increases, growing faster than any exponential, but slower than e raised to x. The derivative of x raised to x uses the technique of logarithmic differentiation. Let y equals x raised to x. Take the natural log of both sides. Natural log of y equals x times natural log of x. Differentiate both sides with respect to x. The left side gives 1 over y times dy over dx. The right side gives natural log of x plus x times 1 over x equals natural log of x plus 1. So 1 over y times dy over dx equals natural log of x plus 1, which means dy over dx equals y times the quantity natural log of x plus 1 equals x raised to x times the quantity natural log of x plus 1. This derivative is positive for x greater than e to the negative 1, confirming the function increases after its minimum. At large x, the derivative grows like x raised to x times natural log of x, which is nearly as fast as the function itself, indicating rapid growth. The function x raised to x is even more extreme. Here we have a tower of height 3. Evaluating at x equals 2 gives 2 raised to 2 raised to 2 equals 2 raised to 4 equals 16. At x equals 3, we get 3 raised to 3 raised to 3 equals 3 raised to 27, which is already in the trillions. Such rapidly growing functions appear in combinatorics, in counting certain structures or configurations. They also appear in theoretical computer science, measuring the complexity of certain algorithms, or the resources needed to solve certain problems. The inverse of these functions, the superlogarithms, or iterative logarithms, grow incredibly slowly. The function log star of x, the number of times you need to apply logarithm to reduce x to 1 or less, grows so slowly it might as well be constant for practical purposes. For x up to e raised to e raised to e raised to e, we have log star of x, at most 5. These ultra-slow growing functions appear in algorithm analysis. Some algorithms have running time proportional to n times log star of n, which is essentially linear for any realistic n. The log star is theoretically present but practically invisible. Between the extremes of super-exponential growth and super-logarithmic slowness lies the realm where most interesting functions live. Linear, quadratic, cubic growth, exponential, logarithmic, square root. These are the functions we encounter in applications, the ones that model real phenomena at human scales. But the extreme functions remind us of the breadth of possibility. Mathematics contains functions growing and decaying at every conceivable rate. The hierarchy is rich and infinite. No matter how fast a function grows, we can construct one that grows faster. No matter how slowly, we can construct one slower. This open-endedness is part of what makes mathematics inexhaustible. There's always something beyond what we've considered. Always another level of complexity or simplicity to explore. Let's think about the exponential from yet another angle, through generating functions. The generating function encodes a sequence as a power series. If we have sequence a 0, a 1, a 2, and so on, the generating function is the sum from n equals 0 to infinity of a sub n times x to the n. For the sequence of all 1s, 1, 1, 1, 1, the generating function is the sum of x to the n, which equals 1 over 1 minus x for the magnitude. At x less than 1, this geometric series is the simplest generating function. For the sequence in factorial, we get the sum of n factorial times x to the n. This series doesn't converge for any x not equal to 0 in the usual sense, but we can work with it formally, manipulating it algebraically without worrying about convergence. The exponential generating function of a sequence uses x to the n over n factorial, instead of just x to the n. For the sequence a sub n, this is the sum of a subs m times x to the n over n factorial. The exponential generating function of the sequence of all 1s is the sum of x to the n over n factorial equals e raised to x. So the exponential generating function of the sequence is all 1, 1, 1. This connects the functions at combinatorics, The nth coefficient, divided by n factorial, counts something related to permutations or arrangements. For the sequence in factorial, the exponential generating function is the sum of n factorial times x to the n over n factorial equals the sum of x to the n equals 1 over 1 minus x. So the ordinary generating function of factorials doesn't converge, but their exponential generating function is simple. These generating functions let us solve recurrence relations, count combinatorial objects, and translate between different representations of sequences. The exponential function appears whenever we're counting labeled structures, where the order of elements matters. In graph theory, the exponential generating function of connected graphs on n-labeled vertices involves the exponential function. The function e raised to x times the quantity e raised to x minus 1 minus x appears in formulas for counting various graph properties. These applications might seem far from the original conception of exponentials as growth functions, but they're united by the underlying mathematics. The exponential encodes information about factorials, about repeated operations, about structure building on itself. We could also discuss the exponential function's role in Fourier analysis more deeply. The Fourier transform takes a function f of x and produces the function f of omega equals the integral from negative infinity to infinity of f of x times e raised to negative I times omega times x with respect to x. This transform decomposes f into its frequency components. This function e raised to negative I times omega times x oscillates at frequency omega. Integrating f times this oscillation gives the amplitude of that frequency in f. The inverse Fourier transform reconstructs f from its frequency components. F of x equals 1 over 2 pi times the integral of f of omega times e raised to I times omega times x with respect to omega. These transforms are inverse to each other, up to constants. They convert between time and frequency, between position and momentum, between different representations of the same information. The exponential function, with its dual role as growth function and oscillation, is the kernel that makes this work. It's the eigenfunction of differentiation, the bridge between addition and multiplication via logarithms, the generator of rotations in the complex plane. All these roles stem from the single defining property, being equal to its own derivative. From this, everything else follows. The series expansion, the complex behavior, the connections to differential equations in Fourier analysis, all emerge from that one fact. In a sense, the exponential function is the simplest non-trivial function. Polynomials are simpler, but they don't capture dynamics. Constants are simpler still, but they don't capture change at all. The exponential is the first function that's truly alive, that embodies growth and change in a fundamental way. When we nest exponentials, creating towers of compositions, we're exploring how complexity emerges from simplicity. Each layer adds another level of indirection, another fold in the function's behavior. The result grows faster, oscillates more wildly, becomes harder to analyze. But even the most complex exponential composition is still built from the same simple pieces. It's still differentiable, still analytic where it's defined, still subject to the rules of calculus and complex analysis. The tools we use to understand simple functions still apply, though the calculations become more involved. This is a common pattern in mathematics. We start with simple objects and simple operations. We combine them in increasingly complex ways. The combinations inherit properties for the pieces, but exhibit new emergent behaviors. Understanding both the inheritance and the emergence is the challenge. Exponentials exemplify this pattern. They're simple in isolation, profound in combination, inexhaustible in variation. They connect discrete and continuous, algebraic and analytic, real and complex. They model growth and decay, oscillation and rotation, stability and chaos. In some ways, the entire edifice of calculus rests on exponentials. Derivatives and integrals, series and limits, differential equations and transforms, all involve exponentials at their core. Learning to work with exponentials is learning to work with change itself, and that's what calculus is ultimately about. Understanding how things change, how one quantity depends on another, how small differences accumulate into large effects, how local information determines global behavior. The exponential function, in its own derivative, is the fixed point of differentiation. It's the function that change doesn't change, that remains itself under the operator that measures change. This paradoxical stability, while embodying change, makes it central to the entire subject. As we've seen, even restricting to real numbers, exponentials are rich. Adding complex numbers multiplies that richness. The plane becomes a landscape of growth and rotation, magnitude and phase, zeros and poles, and essential singularities. Generalization opens new vistas. Matrix exponentials for systems of equations. Operator exponentials for quantum evolution. Exponential maps in Lie theory connect to algebra and geometry. The concept extends far beyond the elementary function we started with. Yet all these generalizations preserve the core property. Exponentials are the solutions to equations of the form derivative equals constant times function. In one dimension, scalar equations. In many dimensions, matrix equations. In manifolds, operator equations. The pattern persists across contexts. This universality suggests we're touching something fundamental about mathematics itself, not just about a particular function. The exponential represents something deep about how structures build on themselves, how recursive processes unfold, how symmetry and dynamics intertwine. In the end, studying exponentials is studying the mathematics of becoming, of process, of change. It's looking at the world not as static configurations, but as flows and transformations. This perspective pervades modern mathematics and physics, from dynamical systems to quantum field theory. The function e raised to x, simple as it appears, contains multitudes, its derivatives, its integrals, its series, its values. All tell us something about the nature of growth and change. When we compose it with itself, we see how complexity emerges from iteration. When we apply it to matrices or operators, we see how it organizes higher dimensional dynamics. Every time we encounter an exponential in mathematics, we're meeting an old friend in a new guise. The function might be wearing different clothes, might be playing a different role, but it's the same underlying structure. Recognizing it, understanding its properties, using it effectively, these are core skills in mathematical thinking. And beyond pure mathematics, exponentials shape how we understand the world. Population dynamics, compound interest, radioactive decay, electrical circuits, temperature change, all follow exponential patterns. Learning to recognize and work with these patterns is learning to think quantitatively about change. So while this exploration is focused on mathematical properties, the implications extend far beyond. Exponentials are tools for thought, frameworks for understanding, bridges between abstract theory and concrete application. The journey from e raised to x through e raised to x, and beyond traces a path from elementary to advanced, from simple to complex, from familiar to strange. But it's all continuous, all connected, all part of the same mathematical landscape. Understanding that landscape, being able to navigate it, seeing how different regions connect and differ, that's what mathematical maturity looks like. It's not about memorizing formulas or techniques, though those help. It's about seeing structure, recognizing patterns, understanding why things work the way they do. Exponentials offer a perfect case study in this kind of understanding. They're simple enough to grasp quickly, but deep enough to repay extended study. They appear everywhere, connect to everything, reveal new aspects the longer you look. This text has tried to capture some of that richness, to show exponentials from multiple angles, to trace connections between different appearances of the same underlying idea. The goal isn't exhaustive coverage, which would take volumes. It's to give a sense of the landscape, to point out interesting features, to encourage further exploration. Mathematics is infinite. We can never see all of it, but we can see enough to appreciate its structure, to navigate confidently within familiar regions, to venture into new territories with some idea of what to expect. Exponentials are an excellent region to know well. They're central, well-connected, beautiful in their own right. Spending time here, understanding the terrain, pays dividends throughout mathematics and beyond. As this section closes, the exponential function remains, as it has always been, fundamental and inexhaustible. Each encounter reveals something new. Each application shows another facet. The function that equals its own derivative, that bridges growth and rotation, that solves so many equations and models, so many phenomena, continues to surprise and enlighten. The river of mathematics carries us deeper now, past the familiar banks where linear thinking once felt sufficient. Here, in the territories beyond straight lines, something fundamental shifts. The world reveals itself not through addition and subtraction, not through the patient accumulation of equal steps, but through multiplication upon itself, through growth that feeds upon growth, through change that accelerates its own unfolding. You already know this feeling, even if you haven't named it mathematically. It's the way a rumor spreads through a room, gathering momentum. It's the way your savings account grows when compound interest begins its quiet work. It's the way a single candle, if it could ignite others, might fill a darkening chamber with exponential brightness. What starts small becomes vast not through patience alone, but through a peculiar kind of self-reinforcement. Let's return to something fundamental before we venture further. When we multiply the same number by itself, we've already touched upon powers. 2 to the third power means 2 times 2 times 2, which gives us 8. This is straightforward enough. But here's where exponentials begin their whispered song. What happens when we take a number, any number really, and we ask what power of that number gives us something else entirely? If 2 to the third power equals 8, then the reverse question becomes, what power of 2 equals 8? The answer is 3. We call this the logarithm. It's the shadow cast by exponentiation, the question asked backward. The logarithm of 8 with base 2 is 3. It's denoted as log base 2 of 8 equals 3, though we'll speak it plainly. The logarithm, base 2 of 8 is 3. This inverse relationship echoes through much of what follows. Exponents and logarithms dance together like partners who have known each other for centuries. Where one builds upward, the other maps that building, measures it, understands its architecture. Exponentiation is the process of climbing. Logarithms are the way we count the steps afterward. But let's dwell in the realm of exponentials themselves for a moment, because something extraordinary lives there. Consider the scenario. You have a culture of bacteria, small invisible organisms that reproduce by splitting, doubling their numbers with each generation. If you begin with a single bacterium, and each hour it duplicates, then after 1 hour you have 2, after 2 hours you have 4, after 3 hours 8, after 4 hours 16. Each hour the population doubles, and this doubling accelerates the total in a way that multiplication cannot quite capture. This is 2 raised to the power of time. If t represents hours, then the population is 2 to the power t. After 10 hours you have 2 to the 10th power, which is over 1,000 bacteria. After 20 hours you have more than 1,000,000. After 30, over 1,000,000,000. The numbers don't increase, they explode. They burst beyond the confines of reasonable expectation. Now Natch is something different. Instead of doubling, suppose each hour the population multiplies by 1.1. This is a 10% increase per hour, modest and seemingly gentle compared to doubling. 1.1 to the power of t, where t is hours. After 1 hour you have 1.1. After 2 hours, 1.1 times 1.1, which is 1.21. The growth seems slow at first, glacially slow, compared to doubling. But here's where exponentials reveal their patient cruelty. Wait long enough, and the 10% growth catches up and surpasses almost everything else. After 70 hours, 1.1 to the 70th power becomes roughly 1,300. After 140 hours, roughly 200,000. The slower growth merely postponed the inevitable acceleration, the point where small gains compound into overwhelming magnitude. This is perhaps the deepest insight about exponentials. The base number matters far less than time itself. The growth rate of 1.005, that's 0.5% per period, seems trivial, almost nothing. Yet applied repeatedly, over centuries or millennia, even 0.5% becomes remarkable. The formula expresses this in its simplest form. If you start with an initial amount, let's call it A, and it grows by a rate r each period, after n periods you have A times the quantity 1 plus r raised to the power n. The 1 plus r is the multiplier each period. 1 plus r of 0.1 would be 1.1. 1 plus r of 0.05 would be 1.05. But mathematicians discovered something curious. There's a special number that emerges natural when you ask a particular question. What happens if you compound continuously, infinitely often, rather than at discrete intervals? Imagine taking $1 and applying interest at 100% per year. After 1 year, you have $2. Straightforward. But what if the bank compounds monthly? Then each month you earn roughly 1 divided by 12 of that annual rate, which is 1 divided by 12 times the dollar, or roughly 0.083 cents. After a month, you have 1 plus 1 divided by 12, approximately 1.0833. After 12 months, you have 1 plus 1 divided by 12 raised to the 12th power. 1 plus 1 divided by 12 to the 12th power is approximately 2.61 cents. More than doubling, because the interest you earn in the first month itself earns interest in the second month, and so on. What if compounding happens daily? Then you have 1 plus 1 divided by 365, raised to the power 365. This yields approximately $2.71. Weekly, hourly, each increase in compounding frequency produces more growth. The sequence climbs higher. 2 becomes 2.16, becomes 2.59, becomes 2.71. But this sequence doesn't climb indefinitely. It approaches a limit, a number it gets arbitrarily close to, but never quite reaches. This number is called e, and it's one of the most important constants in all of mathematics. It begins 2.71828, and the digits continue forever, never repeating, never settling into a pattern. We can calculate it to any precision we want, but we'll never write it down completely. The number e is approximately 2.718. It emerges from this limiting process of continuous compounding, but it appears elsewhere too, in the mathematics of growth and decay, in the shapes of hanging chains, in the vibrations of springs, in the populations of living things, in the cooling of hot objects, in the discharge of capacitors. It threads through the physical world like an invisible pattern that mathematics only later discovered was already there. Once he exists as a concept, exponentials take on a more complete form. When we talk about exponential growth in its purest sense, we usually mean e raised to some power. Growth that follows e to the power of k times t, where k is a growth rate and t is time, is called natural exponential growth. Natural not because it's the simplest, but because it appears naturally in the laws of physics and biology and chemistry. This is where the whispered quality of exponentials becomes truly audible. Consider a substance that decays radioactively. Each atom has a certain probability of decaying in any given time interval, but which particular atom will decay is utterly random. Yet taken as a whole, the population of atoms follows a pattern. The number remaining after time t is the initial number times e raised to the negative power of lambda times t, where lambda is the decay constant of that particular substance. For uranium-235, lambda is extremely small, so the negative exponent changes very slowly. After a billion years, only half the uranium has decayed. For carbon-14, lambda is larger, so the decay is faster. After roughly 5,700 years, half of any carbon-14 sample has become nitrogen. This is the basis of radiocarbon dating. By measuring how much carbon-14 remains in ancient organic material, we can calculate how long ago that organism was alive. The equation that describes this decay is deceptively simple. N of t equals n naught times e raised to the power negative lambda t. N of t is the amount remaining at time t. N naught is the initial amount. The negative in the exponent ensures that as t increases, the exponent becomes more negative, and e raised to a negative power is less than 1, so the amount decreases. Elegant. Economical. The entire process of radioactive decay, one of the fundamental processes of the universe, condensed into a single formula. But let's turn to growth, which carries a different emotional weight. Suppose you place $1,000 in an account that earns interest at a rate of 5% per year, compounded continuously. The amount you have after t years is 1,000 times e raised to the power of 0.5 times t. After 1 year, you have 1,000 times e to the 0.05, which is approximately 1,000 times 1.0513, so roughly $1,051. After 10 years, you have 1,000 times e to the 0.5. The exponent is a half, so you're taking the square root of e roughly, since e to the half power means e to the power of 1 divided by 2. The square root of e is approximately 1.649. So you have roughly $1,649. After 50 years, you have 1,000 times e to the 2.5. Now e is raised to a much larger power. E to the 2.5 is approximately 12.18. Your investment has grown to roughly $12,180. The 5% annual rate, compounded continuously, turns $1,000 into $12,000 over 50 years. More than a tenfold increase. This is not magic. It's mathematics expressing what happens when something feeds on itself, when the growth itself becomes capable of growing further. But it illuminates something unsettling about the world. Small differences in growth rates, over long enough timescales, produce enormous differences in outcomes. Imagine two countries, each with an initial economy of $1 trillion. Country A experiences annual growth of 3%. Country B experiences annual growth of 2%. The difference is 1 percentage point, minimal, seemingly negligible. After 1 year, A has roughly 1.03 trillion, and B has 1.02 trillion. The difference is about 10 billion, noticeable, but not vast compared to the total. After 20 years though, A has roughly 1.8 trillion, while B has roughly 1.49 trillion. A has become substantially wealthier. After 50 years, A exceeds 2.6 trillion, while B remains below 2.6 billion. Wait, let me recalculate that. After 50 years, A exceeds 2.6 trillion, while B remains below 2 trillion. A is now more than 30% wealthier. After a century, the gap has widened to something almost atomic in its disparity. A has grown to 19 trillion, while B has grown to roughly 7.1 trillion. 1 percentage point of annual growth rate, sustained over a century, produces a difference of $12 trillion. Compound growth of different magnitudes, even slightly different magnitudes, eventually produces different worlds. This observation has profound implications. It suggests that the trajectory of a system matters more than its current state. A small change in growth rate, applied consistently, reshapes everything. This is why economists obsess over growth rates, why even small changes in interest rates can affect entire markets, why the difference between 2.0% and 3.0% is not merely numerical, but ideological, a statement about what kind of world we're living in. Now let's consider what happens when exponentials meet their opposite. Imagine you're trying to solve an equation where the unknown appears in an exponent. For instance, you know that 2 raised to some power equals 32, and you need to find that power. The answer, as we said before, involves logarithms. The power is log base 2 of 32, which equals 5, because 2 to the 5th power is indeed 32. But solving equations where the unknown is in the exponent requires logarithms, even when the numbers are less convenient. Suppose 2 raised to the power x equals 10. We need to find x. We can't find a clean integer, because 2 to the 4th power is 16, which is too big, and 2 to the 3rd power is 8, which is too small. The answer lies between 3 and 4. To express it exactly, we write it as log base 2 of 10. This logarithm, evaluated numerically, is approximately 3.32. You can verify this by taking 2 to the power 3.32, which gives roughly 10.02. Logarithms transform exponential equations into linear ones, which is why they're so valuable. If you're dealing with exponential growth, but want to understand the underlying rate, you take logarithms. If you're charting the course of something that grows exponentially, logarithmic scales help you see the pattern, instead of watching everything compress into an incomprehensible curve. A logarithmic scale works by spacing distances, not according to equal additions, but according to equal multiplications. On a linear scale, the distance from 1 to 2 is the same as the distance from 2 to 3. On a logarithmic scale, the distance from 1 to 2 corresponds to a multiplication by 2. The distance from 2 to 4 also corresponds to a multiplication by 2, so those two intervals are equal, even though the absolute differences are different. This makes it possible to visualize things that span many orders of magnitude on a single graph. The Earth's surface covers about 500 million square kilometers. A single grain of sand might occupy about 1/100th of a square millimeter. These numbers span more than 18 orders of magnitude. On a linear scale, the sand grain would be invisible. On a logarithmic scale, they occupy comparable positions, and we can see the relationship between them. Different bases for logarithms serve different purposes. We've mentioned base 2, which arises naturally in computing and information theory. Base 10 logarithms, called common logarithms, once dominated practical calculation and scientific work. But the natural logarithm, logarithm base e, carries the most theoretical weight. The natural logarithm, usually written as ln, is the inverse of the natural exponential function, e raised to the power x. If you know that e raised to the power y equals some number z, then the natural logarithm of z is y. The two are mirror images. This relationship means that natural logarithms inherit many beautiful properties from exponentials. The logarithm of a product is the sum of the logarithms. The logarithm of a quotient is the difference of the logarithms. The logarithm of a number raised to a power is the power times the logarithm of the number. These properties transform multiplicative relationships into additive ones, which is why logarithms were so valuable for computation before calculators existed. A table of logarithms, combined with these properties, could turn tedious multiplication into simple addition. But beyond utility, logarithms reveal something fundamental about how quantities relate across different scales. In biology, the sensitivity of organisms often follows logarithmic relationships. Your perception of brightness, for instance, doesn't increase linearly with light. A lamp 10 times brighter doesn't seem 10 times brighter to your eyes. Instead, your perception follows a logarithmic curve, so a lamp 100 times brighter might seem only twice as bright. This is why sound levels are measured in decibels, a logarithmic scale. An increase of 10 decibels represents a tenfold increase in sound intensity, but the perceived loudness increases much less dramatically. This logarithmic quality of perception suggests that exponentials describe growth in certain physical quantities, while logarithms describe how we experience those quantities. The external world may explode in exponential fashion, But our consciousness often filters it through logarithmic perception, compressing the vast extremes into something manageable, something our minds can accommodate. The interplay between exponentials and logarithms becomes particularly intricate when we consider derivatives, the calculus tool that measures how quickly something changes. The derivative of e raised to the power x is e raised to the power x itself. No other function has this property. The rate of change of the natural exponential function is the function itself. This seems almost circular, almost impossible. Yet it emerges perfectly from the definition. What this means concretely is that the natural exponential function describes its own rate of change. If something grows exponentially with e as its base, then the speed at which it's growing at any moment is proportional to how much is there. The bigger it gets, the faster it grows. This is the essence of feedback, of positive reinforcement, of systems that accelerate their own expansion. Conversely, the derivative of the natural logarithm of x is 1 divided by x. This is much simpler than you might expect, and it shows that logarithmic functions change more slowly as they grow. As x becomes larger, the rate of change of the logarithm becomes smaller and smaller. The logarithm grows, but ever more slowly, asymptotically approaching a kind of steady state, where each additional unit of x produces less and less change in the logarithm. This differential relationship illuminates a crucial observation. Exponential growth becomes increasingly difficult to manage or reverse because the rate of growth accelerates. A logarithmic process becomes easier to manage as it develops, because the rate of change slows. They're opposite in character, not just in being inverses of each other, but in how they unfold over time. Now, exponentials don't always grow. The number 1.05 raised to increasing powers grows larger, as we discussed. But 1 divided by 1.05, which equals roughly 0.952, raised to increasing powers, gets smaller and smaller. 0.952 to the power of 1 is 0.952. To the power of 2 is roughly 0.906. To the power of 10 is roughly 0.61. To the power of 20 is roughly 0.37. To the power of 100 is something infinitesimally close to 0. This is exponential decay, and it describes countless processes. The fading of light as it passes through an absorbing medium, the cooling of a warm object in a cold room, the loss of memory over time without reinforcement, the radioactive decay we mentioned before. The formula is identical in structure, just with a base between 0 and 1 instead of greater than 1. When the base is between 0 and 1, you can also write the formula using e and a negative exponent. 0.952 to the power of t is equivalent to e to the power of negative 0.051 times t, approximately. The negative in the exponent encodes that we're dealing with decay rather than growth. This matters because it unifies all exponential processes under a single conceptual umbrella. Whether growing or decaying, whether you're dealing with bacteria populations or radioactive atoms, the mathematical structure remains consistent. You have an initial amount, a rate, and time. The formula adapts to describe what happens. This universality is part of what makes exponentials so powerful in modeling the real world. Let's consider a practical problem that draws together these threads. Suppose you borrow $10,000 at an interest rate of 6% per year, compounded monthly. How much do you owe after 5 years? The formula is principal times 1 plus the annual rate divided by the number of compounding periods. The whole thing raised to the power of the number of periods times the number of years. So you have 10,000 times 1 plus 0.06 divided by 12 raised to the power of 12 times 5. That's 10,000 times 1 plus 0.005 raised to the power of 60. That's 10,000 times 1 plus 0.065 to the power of 60. Now, 1.005 to the power of 60 requires calculation. We can use logarithms. The logarithm of 1.005 to the power of 60 is 60 times the logarithm of 1.005. The natural logarithm of 1.005 is approximately 0.00499. 60 times that is roughly 0.2994. E raised to the power of 0.2994 is approximately 1.3489. So 1.005 to the power of 60 is roughly 1.3489. 10,000 times 1.3489 is $13,489. Over 5 years, the original loan has grown by more than 34%, simply due to compounding interest. If you'd borrowed at a rate compounded annually, instead of monthly, the calculation would be slightly different. 1 plus 0.06 to the power of 5 is 1.06 to the fifth power, which is approximately 1.3382. That would give you $13,382, slightly less. Continuous compounding would give even more, 10,000 times e to the power of 0.3, which is roughly $13,498. The differences seem minor, but they compound over longer timescales and higher rates. This is why the compounding frequency matters to lenders and borrowers, why credit card companies highlight it, why understanding exponentials becomes a matter of personal finance, and not merely abstract mathematics. Moving toward more abstract territory, we can ask what happens when we take exponentials of complex numbers, those entities that include the imaginary unit I, the square root of -1. If you raise e to the power of I times some angle, expressed in a unit called radians, something remarkable occurs. The result is a complex number whose real part is the cosine of that angle, and whose imaginary part is I times the sine of that angle. This is Euler's formula, named after Leonhard Euler, one of the most prolific mathematicians who ever lived. E to the power of I times theta equals cosine of theta plus I times sine of theta. This formula is often called the most beautiful equation in mathematics, and with reason. It connects exponentials to trigonometry, imaginary numbers to real geometry, in a relationship that seems almost too perfect to be true, yet follows inevitably from the definitions. Using Euler's formula, you can express the sine and cosine functions in terms of exponentials. Cosine of theta is the real part of e to the power of I times theta. Sine of theta is the imaginary part of e to the power of I times theta, divided by I. This means that trigonometric functions, which describe the oscillations of waves and circles, are secretly exponentials in disguise when you allow complex numbers into the picture. Furthermore, Euler's formula implies that e to the power of I times pi equals -1. That is, e raised to the power of I times pi, where pi is the famous circle constant approximately 3.14159, equals -1. This is astounding. The exponential of an imaginary multiple of pi gives you a negative real number. The identity brings together 5 fundamental constants: 0, 1, I, pi, and e, in a single elegant relationship. A complete expression of this identity, setting up the equality to -1, and then adding 1 to both sides to get 0, gives you an equation with all 5 of those fundamental constants. The fact that exponentials with imaginary exponents produce oscillations, rather than monotonic growth or decay, opens up enormous possibilities. Any oscillating motion, any wave, any periodic phenomenon, can be expressed using exponentials with imaginary exponents. This is why Fourier analysis, which decomposes complex waves into sums of simpler oscillations, relies on these exponentials. A complicated waveform, no matter how irregular, can be expressed as a sum of pure exponential oscillations at different frequencies and amplitudes. This is the heart of signal processing, of how we understand and manipulate sound, light, radio waves, and countless other phenomena. In this way, exponentials become a universal language for describing change. Growth, decay, oscillation, these are all just different facets of the exponential function viewed from different angles. Literal and metaphorical. Real bases greater than 1 give growth. Real bases between 0 and 1 give decay. Complex bases give rotation and oscillation. It's all exponentials, yet they manifest in radically different ways. This versatility extends into differential equations, the mathematical statements that relate quantities to how quickly they're changing. Many of the most important differential equations in physics, chemistry, biology, and engineering have solutions that are exponentials or combinations of exponentials. The simple differential equation that states the rate of change of something is proportional to the amount of something itself has the solution that the amount grows exponentially. This equation and its solution describe chemical reactions that follow first-order kinetics, the growth of populations under certain conditions, the cooling of objects, and much more. More complex systems often have solutions involving exponentials with complex exponents, which bring in oscillations. The motion of a pendulum, the vibrations of a drum, the behavior of electrical circuits, all can be described by differential equations, whose solutions involve exponentials with imaginary parts. The interplay of exponential growth with imaginary exponents produces the familiar sine and cosine waves, the patterns we perceive in nature again and again. Consider the motion of a damped oscillator, something like a weight on a spring in a viscous medium. Initially the weight might swing back and forth, but friction, or the resistance of the medium, gradually reduces the amplitude of the oscillations. The solution involves an exponential decay multiplying an oscillating term. The exponential decay, which goes to zero over time, modulates the oscillation, causing it to die out. This describes countless real systems: a pendulum in air, a drumhead after being struck, the current in an electrical circuit with resistance. There are also forced oscillators, where some external force periodically pushes the system. The mathematical solution often reveals resonance. Certain frequencies of forcing produce much larger oscillations than others, because the driving frequency matches the natural frequency of the system. This is why bridges can collapse, if marching troops keep time, why opera singers can shatter glass, why certain frequencies of vibration will cause an aircraft to fail. Exponentials and oscillations, combined, reveal these dangerous harmonies. Much of the world's technological infrastructure rests on understanding these exponential and oscillatory processes. Radio transmitters use oscillating exponentials to generate waves at specific frequencies. Radar uses the same waves to detect objects. Your body's nervous system uses exponential processes to transmit electrical signals. Your ears perceive sound through oscillatory vibrations that follow exponential decay patterns in amplitude. The life from electronic devices involves oscillations at frequencies so high they're invisible, but still fundamentally exponential in nature. Stepping back to get some perspective, it's remarkable how much territory exponentials cover. They describe the uncontrolled growth of populations, the controlled release of drugs into your bloodstream, the intensity of earthquakes, the brightness of stars, the decay of unstable particles, the behavior of stock markets, the spread of diseases, the rate at which you forget information. Pick almost any phenomenon in the natural or human-made world that changes over time, and there's likely an exponential lurking somewhere in its mathematical description. This ubiquity arises because exponentials emerge naturally whenever you have feedback, self-reinforcement, or systems where the rate of change depends on the current state. Bacteria reproduce more when there are more bacteria. Money earns interest on the interest it's already earned. Diseases spread faster when there are more infected individuals. Heat flows faster from hot objects because they're hotter. In each case, the more you have, the faster you produce more. That's the signature of exponential behavior. The challenge of exponentials, when they describe growth, is that they scale so quickly that human intuition fails. Our brains evolved to reason about linear and polynomial relationships, things that change at relatively steady rates. Exponentials violate that intuition. A trickling in growth rate might seem like modest change, but if it's a growth rate per year, after 20 years it will have produced a doubling of the final result compared to the smaller rate. Over a century, it would be orders of magnitude different. We underestimate exponentials, which is why exponential growth surprises us, why we're slow to respond to exponentially developing crises, why we consistently overestimate what we can do in a year, and underestimate what we can do in 5 years or 10. Understanding exponentials, truly internalizing their behavior, requires shifting from intuition to calculation, from expectation to mathematical prediction. This is difficult but crucial. The trajectory we're on, whether with disease spread, resource depletion, technological capability, or climate change, involves exponential or near-exponential components. Making good decisions about these trajectories requires not merely knowing the formulas, but grasping what they mean for outcomes decades hence. The logarithm becomes our tool for taming this intuitive failure. By taking the logarithm of exponential quantities, we transform the exponential curve into a straight line. On a logarithmic scale, exponential growth appears as a constant slope. This makes it easier for our linear intuition brains to perceive what's actually happening, to extrapolate, to plan. It's a kind of mathematical translation, converting the foreign language of exponentials into something our minds can grasp. Exponentials also reveal something about competition and dominance in complex systems. If two processes both grow exponentially, but at different rates, eventually, the faster one dominates overwhelmingly. A system growing at 3% per year will eventually dwarf one growing at 2% per year. A species reproducing faster will eventually crowd out competitors. A technology improving exponentially will obsolete its predecessors. The future belongs to exponential processes, and specifically to whichever exponential process has the edge, however small, in its rate. This has enormous implications for evolution, economics, technology development, and strategy. Small advantages in reproduction, growth rate, or efficiency, when sustained over long timescales, become massive advantages. Conversely, small disadvantages become irreversible handicaps. A company that innovates 2% faster, a species that reproduces even slightly faster, a military that develops weapons even marginally more effective. These entities eventually dominate their domains utterly. Evolution is filled with examples of species that found a niche, reproduced rapidly, and displace everything else. Markets are filled with companies that achieved exponential advantages and became monopolies. The arms race dynamic arises precisely because exponential growth of capabilities produces existential dominance. Understanding exponentials means understanding the deep drivers of change in the world. It means seeing that small differences, maintained consistently, become the difference between worlds. It means appreciating that you cannot reason about long-term trajectories using linear intuition. It means accepting that some futures are inevitable if we stay on current exponential paths, unless the path itself changes. There's something almost melancholic about exponentials, viewed from this angle. They promise unlimited growth, yet growth that accelerates, that demands resources, and space and time without mercy. They describe cooling objects that gradually reach thermal equilibrium with their surroundings. They describe learning curves that improve dramatically at first, then plateau. They describe diseases that spread unchecked until they run out of susceptible hosts. They describe both expansion and inevitable limitation, often in the same formula, with merely a sign difference. The most profound lesson exponentials teach might be that change is not uniform. The future will not be like the past extended. The rate of change itself changes, accelerates, transforms. Systems that seem stable harbor exponential dynamics waiting to be unleashed. Bubbles form when exponential growth rates encounter limits. Collapses occur when exponential decay rates accelerate. Revolutions happen when exponential change becomes visible to everyone simultaneously. We live in an age increasingly shaped by exponential processes. Moore's law, the observation that the number of transistors that can fit on a chip doubles roughly every 2 years, describes exponential improvement in computing power. Artificial intelligence systems are improving exponentially in capability. The global population, though growing more slowly now, grew nearly exponentially through much of history. Resource consumption, both of renewable and non-renewable resources, has followed exponential curves. Understanding these exponentials, and their limits, may be the defining task of our generation. The mathematics of exponentials is beautiful, almost ineffably so. But the reality of exponentials, the way they drive the actual world we inhabit, demands respect and even caution. They are not mere abstractions. They are forces that will reshape everything, unless we understand them deeply enough to guide them toward outcomes we actually want, rather than outcomes that follow inevitably from mathematical laws. That's the bridge between pure mathematics and human consequence, where exponentials become not just equations on a page, but the shape of the future itself.